The title of the paper is Research on a Management Control System in Space-Terrestrial Integrated Network. Introduction. Space-Terrestrial Integrated Network has a series of features such as a broad coverage, flexible networking, non-geographic restriction, and so on. It has received the attention of many countries and industry institutions. At present, a Chinese satellite network is still in the experimental stage. Single satellite telemetry and remote control is still the basic management mode of all satellites, and the industry has not yet designed a metro network management and a control system for the space-terrestrial integrated network. Under the background that satellite network has become an important development trend, the research and the design of management and control system based on space-terrestrial integrated network has important application value and engineering significance. Due to the extremely harsh conditions of satellite communication and the complexity of networking, the management and the control of space-terrestrial integrated network is the key to ensuring the efficient operation of integrated network. The complexity of space-terrestrial integrated network management and control is mainly reflected in some aspects. The first one is complexity of space network environment. Secondly, the complexity of network management technology is an important figure of space networks. The third one is the complexity of space network equipment is another major feature. Network Management Protocol. The Satellite Space-Terrestrial Integrated Network Management Protocol is an improved model derived from the traditional ground network management protocol. Although the satellite network management protocol is more complex due to these specific network characteristics and the special communication environment. It can be analyzed by analyzing the traditional terrestrial network management protocol. The characters, development, application status, and respective advantages and disadvantages of network management are more fully understood. In the model network management system, it mainly includes 4 parts. The first is Network Management System, NMS, and then is Agent, Management Information Base, MIB, and Network Management Protocol, NMP. Its function described is shown in the following table. NMS provides network management and control operation panel for administrator. Agent send the management device information to the network management program in a format and a manner agreed by protocol. MIP define the data structure of the management information on the management equipment and the state mapping the management equipment. NMP define the communication must between the manager and the managed agent and the structure of the information managed library. MMMP proposed in this manuscript is a connection-oriented network management protocol in the application layer. In order to distinguish the transmission series from the lower layer to the connection, the transmission mode of the low layer can be determined by the management entity to negotiate during the establishment of the connection. Therefore, the case that management information is blocked or delayed due to the connection arrangement service of CMIP can be avoided. What's more, the case that management information is not reachable or discarded due to the complete connectionless service supplied by SNMP, which has an obvious impact on the notification of key events and the statistic calculation of indicator parameters. And platform management, source management, perform management, user management, node management, secure management is the 6 parts of the system. Experimental evaluation based on CoNet simulation platform. This manufacturing construct a space-terrestrial integrated network with 100 LEO satellites. On the basis of this simulation platform, the management and control system for integrated network is designed and completed. The efficient control and management of network resources, network platform, and network equipment are realized. The first figure shows that the relationship between the number of get date response received by SNMP, MMP, and the CMIP Network Management System (NMS), and the number of get operation instructions sent by NMS. From the analysis, it can be seen that the CMIP protocol respected by the green line has less package loads and can fully respond to the basic management operations of the management side. obvious package loads because SNMP is for connectless data transmission. The red line represents the TDMA protocol, also has package loads, but not obvious. Basically, able to the response to the management operation of management side. And the second picture shows that the relationship between the member of response state sent by agent of SNMP, TDMA, and CMIP protocol, and the member of GET instruction received. According to the change tree of the green curve, and the agent of CMIP protocol frequently carries out date retrieval operation, which is more obvious when the overhead of management is large. Well, the yellow line table, SNMP protocol, basically does not carry out date retransmissions because SNMP protocol is based on UDP date transmission, does not guarantee the reliability of date transmission. TDMA protocol also has a certain number of retransmission when the network management overhead is large, but does not affect normal network management operations. That is the experiment evaluation. And finally, let's see the conclusion. In the well of the difficulty, complexity, and the resource constraint of the future space integration, network management, and control, this paper designed a multi-domain network management protocol, which can effectively manage the equipment in each management domain of the whole network without increasing network management, reducing network overhead, and ensuring real-time performance. On these basics, an integrated network management and control system is designed and implemented, which is designed and summarized from 6 aspects: platform management, user management, performance management, security management, node management, business management, and so on. And the simulation results shows that the Space-Earth integrated management and control system designed in this paper has a good comprehension performance and efficient, which has important support significance for the construction of the Space-Earth integration network, especially for the Space-Earth integrated management and control. And that is what I want to share with everybody. And thank you for the listening.
Hello everyone, my name is Lu Yang. I'm so pleased to be here to share our study. The paper's name is An Optimist Timer-Based Passive Clustering Algorithm for Vehicular ad hoc Networks. We will introduce our study by these 5 sections. WellNet operates in a challenging communication environment. When are particularly susceptible the hidden node problem. In addition, they must contend with limited spectral bandwidth and a highly variable channel influenced by both stationary and mobile obstructions and interference source. Clustering can be considered as an effective approach to improve routing scalability and reliability. A VNet clustering algorithm works by associating mobile nodes into groups named clusters according to some row site and selecting a node known as the cluster head to mediate between the cluster and the rest of the network in much the same way as an infrastructure wireless access point. The specific function of the cluster head differ depending on the application, as does the method by which it is selected. The clustering algorithm uses the associated node with cluster should ideally be robust to note mobile and sudden change in network and the cluster topology, and should provide reliable end-to-end communication across the VNet. And the next part, typical problem of passive clustering algorithm. Active approaches use a common channel for cluster formation and mating together with other network traffic, like pooling. This can cause contention between clustering traffic and routing traffic, as both compete for finite channel bandwidth. The advantage of passive techniques is that there is no contention between clustering and rolling traffic, allowing the former to assist in achieving the goal of the latter. An active clustering strategy can significantly interfere with the effectiveness of an ad hoc routing protocol due to the additional control overhead required for cluster formation and reformation. By contrast, passive approach exploit the working together between the two systems to achieve cluster formation while avoiding the need for extra traffic. There are also some problems of the traditional PSA algorithm. Problem 1. The communication state of the node in the cluster is unstable and not easy to change. Vehicle chose to join the cluster through priority comparison. The worst node of communication performance is the cluster end node, like Car3. When the network topology changes or cluster merge to increase the number of hops, the communication quality will become very bad, mainly reflecting the node communication delay is too large. Generally, after a node joins a cluster, it will maintain its cluster member identity until the cluster dies or out of cluster head communication range. This makes it difficult for vehicles to get out of this problem and be in poor communication for a long time. Problem 2. When cluster heads are chosen or replaced, most of them will set hysteresis threshold to ensure the stability of clusters. This will make small-scale car groups unable to form clusters. Multiple vehicles may not be cluster head like this picture, but they frequently send out control information requests to join a cluster. At the same time, because there is no cluster head, the vehicle cannot get rid of the decision state. Not only will this cause excessive control information transmission, and broadcast storm. But the vehicle will also fall into a state where they cannot communicate. And problem 3. Because of the characteristic of violent high-speed changes, it will cause instability of the communication link between vehicles. This feature will cause the station where the vehicle on the edge of the cluster communication repeatedly join and exit the same cluster frequently. The result is that the edge vehicle itself cannot stabilize the communication, and it also causes a lot of control information to contain for the channel. And the next section we will introduce optimized timer-based passive clustering algorithm. Firstly, the system model. There are 4 parts. The one is multi-hop. The algorithm takes the multi-hop cluster model. When the node chose the best node to follow, it will evaluate the hop count of the node, and the node will consider the node whose hop count after connection does not exceed the limit hops. Cluster member could connect to cluster head in one hop or multi-hop. The 2 is priority neighbor following strategy. Through priority comparison, the node will follow the strategy of the node with the most stable link in the communication range to form an application. This simple following strategy makes the model algorithm easy to implement. It combines following degree and expect transmission count and expect link lifetime. The 3 is communication routing rule. In the entire network, the vehicle in the cluster member state cannot directly communicate with the RSU and must communicate with the RSU through parent node and the cluster head which they belong to. The cluster head can communicate directly with the RSU or directly communicate with the member of the same cluster in the communication range. This will help to improve the integration of the cluster. The 4 is passive clustering. The algorithm uses passive communication technology. The vehicle does not need to, through active pooling, detect the nodes in the communication range. The node receives the information of the surrounding node by accepting the hello message packet and writes it into the information table. The node information written to the information table has an expiration date timer. The algorithm defines 5 communication states of vehicle in the raw network. Vehicle implement state, switching through algorithm to match their own communication rules and complete their own communication tasks. The 5 communication states is defined as follows. They are IN, IC, CH, CM, and SOCH. We will introduce them later. A recognized standard is needed to determine the cluster head. This algorithm uses the following degree and the average mobility to determine the cluster head. The larger the following degree and the smaller the average mobility is, the more stable the vehicle and the more likely it is to become a cluster head. The cluster formation depends on the change of vehicle node state. The algorithm realizes the orderly communication and the state change of nodes by defining states and timers. The vehicle first enters the IN state and starts a timer of IN. Before the timer expires, the vehicle will continue to maintain IN and continue to send and receive hello message. After the timer experience the vehicle enter the SE state. The vehicle enter the SE state will judge itself to enter the next state, and it will start a timer of SE. It will judge whether it meets the condition of becoming whole CH or CM. If the vehicle has no neighbors, it will enter the ISO-CH state, and if the vehicle does not leave the SE state after the timer SE expires, the node will also directly enter the ISO-CH state. This will solve the problem too. Multiple nodes that cannot be clustered due to the condition BCH will enter ISO-CH state and normally communicate after the timer expires without being stuck in SE. For the CH state, cluster merging may cause the node state to change from CH to CM. When two cluster heads enter communication range of each other, in order to avoid cluster group interference, the cluster groups will be merged. The node with poor performance will give up the CH state and become a follower of the other cluster head. At this time, the two clusters are merged, and the state of this vehicle will also change from CH to CM. In addition, when the CH loss always follows, the cluster will die and the vehicle will enter the ISO-CH state. For the CM state, when the vehicle meets condition CH compared to the following parent vehicle node, the vehicle will enter the CH state. When the vehicle is disconnected from the parent node, or when its communication performance is poor, the node will give up the CH state and enter the ISO-CH state. And this will solve problem 1. For the ISO-CH state, in the traditional algorithm, this state is triggered by parameter changes. It's redefined that this state is no longer triggered by whether or not vehicle knows on a neighbor. Instead, there is a timer of ISO-CH, and the node state must maintain ISO-CH state during this timer. After the timer over time, the state directly changes to the SE state to determine its next state. When the node is in the ISO-CH state, it still receives and sends hello message, but the state change machine is no longer triggered, and the nodes no longer send join request packet to join a cluster. Node will communicate directly through RSU. This can effectively avoid the problem 3. Besides, because when the SE state is changed to the ISO-CH state without neighbors, there only the decision is passed. No control information is sent, and the delay is very small. Therefore, a node that has been in an independent state for a long time under real-world condition can also maintain ISO-CH state for a long time. When there are no neighbors around the nodes, there is less chance of drawing the cluster in a short time, and the timer can be set longer. On the contrary, there are some nodes around the vehicle, but they cannot join cluster because the algorithm limitation. This kind of node has chance to become a state that can join the cluster in a short time, and the timer can be set shorter. We use the Sumo traffic generator and OMNet in the simulation. We compare the communication performance between the OTPCA and the PMCA algorithm. The main V10 simulation parameters setting is shown in Table 1, and the 3 main performance indicators are average transmission delay, average CM duration, and cluster overhead. They can effectively evaluate communication performance of which cluster stability and channel occupied. Usually, the number of nodes hops has the greatest impact on communication delay. The OTPCA allows to scheme up the CM identity to become ISO-CH and communicating directly with RSU. Therefore, the transmission delay of such nodes is relatively low, therefore reducing the average transmission delay. It can be seen from the feature that the average transmission delay increases with the increase of the number of virtues. In addition, it can be seen that the OTPCA algorithm is superior to original PMC algorithm in average transmission delay. And the increase is more obviously in the case of middle traffic load, because in the case of middle traffic load, the vehicle will encounter more problems. In the case of low traffic load, the increasing is relatively small. Most nodes will always in the IN state or one-hop CM state. And most nodes have good communication performance, and most nodes will not actively leave the cluster, so the delay is low and the difference is not obvious. Due to the ISO timer, the node will not frequently change its own state, so as to avoid sending too many control information pockets. Although the probability of collision is potentially increased, the overall control information transmission situation is better than the PMC for the channel. The traditional PC algorithm lacks management of multi-hop nodes, and the communication performance of end nodes is poor. To solve this problem, an optimized timer-based passive clustering algorithm is proposed. Vehicles writing their own communication performance can maintain directly communication mode with RSU or actively exist the cluster. The problem of PC is solved by timer-based on passive technology. OTPCA evaluates and estimates the future communication performance of the nodes from various aspects to determine whether the node should continue to maintain the CM state or disconnect the link. When vehicles cannot join the cluster, OTPCA will make it preferentially maintain an independent state and maintain basic communication through the RSU, and evaluate the surrounding environment, set a timer to decide when to try and join the cluster. Finally, simulation results show that the OTPCA is better than the PMC in average communication delay and cluster overhead. This advantage works best at middle traffic load. At the same time, the average CM duration of the OTPCA is shorter than that of the PMC algorithm. So that's all. Thanks for watching.
Hello everyone, my name is AODMAC and I'm here to present the paper AODMAC, an adaptive and on-demand TDMA-based MAC for vehicular ad hoc networks. And the authors came from the Department of Electronic and Information Engineering, Beihang University, in Haidian District, Beijing. First thing is the presentation outline, and I'll give a little bit about background of the net and some limitations of existing protocols in introduction, and then recap the system model of the MAC, MOMAC, and AODMAC, and compares the key differences among these three protocols, and then give a detailed analysis of our proposed MAC protocol, including the novel structural frame and how adaptive slow set adjustment scheme works, and then through simulation tools, we'll give performance evaluation of these three protocols, and finally followed by the summary and conclusion. So going into the introduction, a vehicle in the near future will be an intelligent unit with onboard units, computers, and communication devices. Vehicular ad hoc networks, that is to say VNet, enable vehicles to communicate wirelessly and form a network autonomously through V2V and V2R links. And the animation illustrates the architecture of VNet. As the position of the safety application is directly related to the safety of people on the road, so the need of a median access control protocol which provides an efficient broadcast service is crucial for VNet. In the literature, various MAC protocols have been proposed for broadcast communication in VNet. However, the existing MAC protocol have some limitations as listed below. First, contention-based MAC such as IEEE or 2.11p are efficient when the number of containing vehicles is small, but the access delay will grow to a significant level when the number of users is large. In addition, the RTS and CTS scheme is disabled in broadcast mode for faster response, which will aggravate the hidden terminal problem. To briefly illustrate the hidden terminal problem, the circle represents the coverage area of a vehicle, and when C is transmitting a frame to B, A is unaware of C's transmission because A and C is unreachable in one hop. Now, if A transmits, its transmission will collide with C's at B. The above problem is called hidden terminal problem, and it is due to C being hidden from A. And hidden means being far away. Go back to a ad hoc MAC. Due to the collision of slow assignment when multiple sets of vehicles move together, which is called merging collision, and the performance of ad hoc will degrade dramatically due to the merging collision. To improve this problem, a very innovative protocol called VMAC is proposed. The VMAC assigns disjoint site of time slot to vehicles moving opposite directions and to RSU, and hence VMAC can decrease the rate of transmission collision caused by node mobility. Furthermore, to make things more excellent, VMAC eliminates the merging collision completely. However, there still exists one common limitation in all these three protocols. That is the efficiency in unbalanced conditions, which is general in realistic road. So the objective of our paper and the presentation is to solve the problem, and we proposed the AODMAC. And then going into the system model, the main idea is that the time is partitioned into what we call frames, frame 1, frame 2, up to frame n in each second, and each frame consists of a constant number of time slots. Then, based on this time partitioning, the TDMA-based protocol allows each vehicle to access at least one time slot in each frame in order to broadcast their safety messages. Specifically, the next three slides will briefly compare the differences of the system model between our proposed MAC with existing MACs. As for VMAC, each frame is partitioned into three sets of time slots, L, R, and F. The F set is associated with RSU, while L and R sets are associated with vehicles moving left and right directions, respectively. So the merging collision caused by the offset mobility can be eliminated. Then thus for WiMAC, which is based on the WiMAC, L and R are further divided into subsets according the number of lines in that direction. So the merging collision can be eliminated completely. But the limitation of this scheme is that once the partition is finished, it is fixed. So it cannot be adaptive to the unbalanced traffic load, and unbalanced means different number of vehicles in different lines. And the unbalanced condition will cause the MAC protocol less efficient and also bring about a channel resource wastage problem. To improve the performance of MAC protocol in unbalanced conditions, our paper devised AODMAC. The key operation is that the partition can adaptively adjust according to the different traffic density in each line. And we illustrate the tablet in the figure below. To facilitate the time slot assignment in distributed and detect collision, each vehicle needs to maintain two things. One is the frame information, and the format of FI is shown below. And the other is a THS table, which includes the information of its neighborhood vehicles in 1 hop and 2 hop range. And the format of THS table is shown below, in which ID equals 0 or line equals 0 means that this slot is unoccupied in 2 hop range. When the vehicle moves on the road, it should update FI and THS table periodically. The process is as shown. Vehicle X will record its current ID, line number, and slot index into FI's first 3 fields. According to the FI, the vehicle can record each FI's first 3 fields into SI. And simultaneously, Vehicle X can record each FI's SI fields into THS table. Based on the above settings, then we can show the capabilities of AODMAC, which slot set size can be adaptively adjusted according to the traffic load in a specific line. We define VLX as a set of 1 hop and 2 hop neighborhoods of vehicle X associated with the line L, and TX as a set of time slots that are reserved by 1 hop and 2 hop range neighborhood in vehicles of vehicle X. And we divide the density into L, M, and H according to the VLX divide NLX. If the value is less than the threshold, you mean DLX is equal to L. If the value is more than threshold, you max DLX is equal to H. Elsewhere, DLX is equal to M. To implement the adaptive slot set adjustment scheme, we divide 2 cases. That is for a non-reserved vehicle and for a reserved vehicle. The concrete procedure is given in the form of the do code. At first, we should compute DLX. And if d lambda x is equal to L or equals to M, we can get this equation. And if d lambda x equals H, we can get these 2 equations. And finally, a non-reserved vehicle can randomly access. And for a reserved vehicle, if the current slot K belongs to its initial slot set, then vehicle X can transmit the package. But if the current slot K not belongs to its initial slot site, and simultaneously d lambda x is equal to L. Vehicle X should acquire a new slot in its initial set. That is to decrease the collision between vehicles. Next, going into the performance evaluation. Our paper used OMNAT++ and Sumer to build simulation platform, and we use C++ as our programming language. And we focus two performance metrics to verify the efficiency of our protocol, which are the rate of transmission collisions and channel utilization. As well, there are 6 simulation conditions including low and balanced, low and unbalanced, medium and balanced, medium and unbalanced, high and balanced, high and unbalanced, respectively. This slide lists some important simulation parameters, include slot duration, transmission range, and simulation time, which equals to 120 seconds, and the figure below shows the real-time simulation seen in OMNAT++ software. Then going into the simulation result. First set of results correspond to first metric, so the figure shows the transmission collision rate versus number of simulations in different traffic conditions. Firstly, in both conditions, no matter in balanced or unbalanced conditions, AOD protocol can achieve the minimum number of collisions and is more effective, especially in high traffic load. The main reason is that AODMAC can adaptively adjust the slow set on demand according to the line density. Secondly, in all 3 different traffic loads, that is to say low traffic load, medium traffic load, and high traffic load, the curves of unbalanced conditions always have more violent fluctuations compared to balanced conditions in VMAC and MOMAC, while it is more stable in AODMAC. Second side of result corresponds to the second metric. So the figure shows the channel utilization versus number of simulations in different traffic conditions. Firstly, based on the same conditions, AODMAC always has a better channel utilization due to its lowest collision rate. Secondly, it has similar performance in balanced and unbalanced conditions under different traffic load, which that is to say low, medium, and high. At last, we find the channel utilization will not monotonically increase. Finally follows the summary and conclusion of the presentation. In our paper, in order to solve the high transmission collisions and channel resource wastage problems in unbalanced traffic conditions of VNet, we proposed an adaptive and on-demand MAC protocol for VNet, named AODMAC. It is a fully distributed MAC protocol. Its frame is partitioned into equal sets according to line numbers, and each line has its own disjoint time slot set for vehicles to access. In AODMAC, the partitioning of each frame is not fixed. Instead, it can be adaptively adjusted according to the different traffic density. Due to each line can acquire its slot site on demand, AODMAC can solve the slot wastage problems in sparse lines and the slot shortage problems in dense lines. Thus, it is efficient in both balanced and unbalanced traffic density scenarios. Simulation results show that the proposed MAC protocol can achieve a better performance than the MAC and MOMAC in terms of transmission collision rate and channel utilization, especially in high traffic load and unbalanced condition. That is the end of my presentation, and thanks for your listening.
The title of the paper is A Dynamic Modified Routing Strategy Based on Load Balancing in LEO Satellite Network. Introduction. With the growth of various types of communication service, terrestrial communication networks have been unable to meet the exploding traffic demands. Satellite networks have broken the limitation of traditional geographic elements and can provide internet access service for any users in the world. The feature that low transmission delay and small size of user terminals have become a new direction for the development of communication infrastructure in the future. In April 2020, satellite internet was included in the list of new infrastructure construction by China and has broad development prospects. Deploying a certain number of satellites in space to provide worldwide internet access service for ground or air users. The development of this system began in the 1980s. Recently, companies such as SpaceX have begun to lead construction of new satellite constellation. Encouraged by relative policies, China has launched a number of LEO satellite constellations such as Hongyun, Hongyan, and so on. As a key technical to enable worldwide service, the routing protocol have been attract many attention, aiming at the problem of load balancing in LEO satellite. This paper proposes a dynamic modified loading balance routing strategy. System model. The LEO satellite network system is mainly composed of three parts: satellite, ground station, and the user terminal. The user terminal initiates the internet access requests and reaches the ground station through the inter-satellite link between the satellite. The ground station serves as a gateway to access the internet. The routing strategy provides service for the path selection of IP data package between the satellite. The data packages are transmitted hop by hop between the satellite, and the routing strategy plays an important role in the reliability of data transmission. In LEO satellite network, the relationship between the neighbors is fixed, but the distribution of ground users is uneven, and the distributions of business traffic is uneven, which is likely to cause the traffic burst. Routing strategy. Step 1. Geographic traffic forecast. Supposing that the number of constellation orbit is n, the number of satellites in each orbit is n. V represents the satellite in the I orbit, and the inter-satellite link between the satellites is represented as E. So the total number of ground user stations are U max. In the initiated state, the flow predicting value F of each satellite node is established, and the mapping relationship between the members of user station U is established as follows. Step 2. Calculation of the weighted shortest path of the entire network routing for forwarding table. At an initiate moment, satellites established 4 links between common and different obeys, while the first obey and last obey do not establish the link, because the movement is opposite. So the total number of intersatellite link is E max. Each link is divided into 2 channels, and the weight of the directional wedge is W. At the next moment, the satellite assigns the obtained weights to the neighbor sites and obtain the direct edge weight of the neighbor sites, and then add weights to the local matrix MD. The matrix format is as follows. Step 3. Priority load balancing dynamic correction. If the load rate is exceeded, or the single queue is exceeded, it is considered that the path is congested. At this time, dynamic routing addressing is started. That is to say, the load rate of a giant satellite is compared. The smaller one is selected as the next hop routing port. The local routing table is revised immediately, and the subsequent IP date packets are forwarding according to the reversed routing table until the next congestion occurred. At that time, in order to avoid loops, it is forbidden to send that package back to the sending port. Performance analyze. Performance analyze adopt the network simulator Exactor, which is developed by Skylab Network Technologies of the United States. The simulation scenery is set according to the parameters of the low Earth orbit constellation, including the global distribution of data streams, ground user terminals, and gateway stations. 3 typical routing strategies. The static routing OSPF and LBRD are compared with the DMLB routing strategy. Packet loss rate, routing time, throughput, and average end-to-end delay are compared. The parameters of LEO constellation, user station, and links parameters is as follows. From the simulation results, it can be seen that packet loss rate of DMLB when the link fails has also no obvious change. The reason is that after detecting the link failure, the satellite node started dynamic calculation and only corrected the next hop. That is, it can avoid the impact caused by link failure, and at the same time replace the newly generated forwarding paths with the originally one to ensure that subsequent date can be forwarded in time after arrival of subsequent date. The source and destination of service are set according to the user station and the gateway station, respectively, and then specify the transmission path for the testing. The total set traffic of source increased from 1 million bit per second to 10 million bit per second. At this time, the link bandwidth limit is reached. As the amount of data set increased, the data throughput received by destination also increased. But static routes have congest more links after exceeding 6 million bit per second, because there is no adjustment mechanism. After congestion occurred in OSPF, the link is disconnected after some quiz on some ports overflow, and OSPF recalculated after that. The flow was increased. The LBRD and the DMLB increased with traffic because the load balancing strategy is adopted to improve the forwarding capacity. So the throughput also increased accordingly. The end-to-end delay is mainly composed of inherent path delay, information processing delay, and queue wait delay. And the end-to-end delay of DMLB remains at a low value because when construction is encountered, only the optimal choice for the next hop does not exceeding change the original path. So the delay is not increased. At the same time, the queue adjustments in DMLB can reduce the delay caused by queuing. Therefore, as the amount of transmission from the source increased, DMLB is not particularly significant increase. Conclusion. This paper proposed a dynamic modified load balancing routing strategy for the low-orbit satellite internet. This strategy used a traffic prediction based on geographic location of the client, used the weighted path length for calculation, and dynamic performance load balancing based on priority. Simulation results shows that this strategy can be quickly and dynamically corrected to reduce the rerouting time and reduce the packet loss rate in case the link fails. What's more, the purpose at DMLB routing strategy can ensure greater throughput and a shorter end-to-end delay under the scenario of link congestion. Thank you for listening.
The current prediction method of low-orbit satellite solar array based on unsupervised learning. I will introduce this paper for 4 parts. First, introduction. Second, algorithm design. Third, example verification. Fourth, conclusion. The output of photovoltaic is impacted by temperature, solar incident intensity, space environment, Earth light, and so many other factors. The max power of solar array output is described as, in all the factors, only the solar incident intensity can be described by mathematics. The other factors are difficult to be described by accuracy mathematics mode. For example, solar array working temperature. The solar array temperature is determined by the following energy equation. This paper proposes a prediction method to low-orbit solar array current based on unsupervised learning to these problems shown above. The advantages of this method are best matching samples through the competition between layers and to calculate the result in form of output function with the best matching samples to obtain the output current of solar array, which effectively avoid the impact factors such as Earth lighting, temperature, and the difference between different satellites analyzed model. The low-orbit satellite solar array output can use the Unify algorithm. The basic idea of this algorithm is to sample the historical current telemetry date according to the certain rules and slice the date to form different sample date. The sample date are cleaned according to the cleaning rules to form a pure sample. The mapping of the sample and the solar cell array output influence factors are established. Each sample corresponds to the influence factors according to the mapping relationship, and the influence factors form the competitive layers of the date. When the currents are predicted, the influence factors corresponding to the period which will be predicted are calculated as the input of the prediction. The matching degree of the computation and input between each computation element in the computation layers, the historical date, which are mapped by the winning computation elements, are the benchmark sample, and the benchmark sample are calculated according to the prescribed functional relationship to form the prediction date. At the same time, the differences between the predicted date and the accurate date are calculated and introduced into the next stage of current calculation as the correction coefficients. In addition to the above factors, The output of the satellite solar array is also affected by the working state and the working mode of the satellite. For example, in the side swing mode, the relationship between the normal sail and the right amount of the sun is changed. At the same time, it may cause the solar sail array shielding by the satellite body and the space-borne equipment. In order to ensure the purity of the sample date, different modes of sample date cause the output of its solar sail array change, which lead to the error in the prediction process. In the process of date selection, the date need to be cleaned to eliminate the interference of the satellite working state, working mode, and so on. The current date set as I. Slice the I according to the rule of orbital period, illumination region, full illumination region, and so on, to form different sets of slice. Current set corresponding to each slice I. If the corresponding state of each date in the II satisfies the set C, or the date is selected as the element of the II set. If there is a situation that the IIG and IIG plus key does not meet the C, the date needs to be cleaned. For the clean satellite solar sail array, current output is set as I. The angle of the incidence is calculated as the current daily distance is R1. The standard distance is R2. Then the distance factor R can be described as this. Each R beta is defined as an impact factor P, and each impact factor Pi will correspond uniquely to the current sample II. The impact factor Pi will map 1 to 1 with the sample II to form a mapping F. Make the Ri beta I as a point Pi on the plane in three-dimensional space. The corresponding relationship between the Pi and the sample II is shown in Figure 2 below, and the corresponding elements of each sample are set as II. The influence factor is defined on the R beta plane, where point Pi mapped to the sample II. The influence factor corresponding to the current period to be predicted is set as P0 on the R beta plane. In this way, the most matching sample P0 with the target point will be obtained and converted to the best match between the mapping influence factor Pi and the input influence factor on the beta R plane. The point Pi on the R beta plane is used as a computation element. and the matching degree between them, the P0 and the winning point P1 in the corresponding sample will be used as the base sample to participate in the calculation of the predicted current. Mark the minimal distance unit after running the competition as Pi. As the benchmark unit for date prediction, take this corresponding date sample, F. According to the mapping relationship between the unit and the sample, each of the corresponding elements in the II will serve as a reference element for the current to be predicted. The predicted current is recorded as the calculation function, Fx. Then the predicted current value, Ia. Two typical satellites with low orbit are selected for verification, which are recorded as S1 and S2. Respectively, two satellites will selected to slide the measured date of solar cell array in 2019, and more than 400 slices will formed. The cleaning rules for the above slice information are C. Post-control date, low state, short state, load current. After cleaning, the number of S1 is 483 and the number of S2 is 409. Table 1 shows that the predict current of satellite S1 and S2 at the sample I3, I35, and the sample I317, I317, I287, I213, respectively. The corresponding elements of each sample are extracted separately and participate in the current calculation to establish the calculation function. Using the above method, the S1 and S2 satellites are calculated to formulate the output current prediction of the solar array at any date, and the current value are shown in Figure 3 and Figure 8 below. It can be seen that the prediction date of the solar cell array current can well reflect the trend of the solar cell array current. In one orbit cycle, expect that the prediction date of the satellite out of ground shadow process can track the actual date well. Analysis of the error between prediction date and the measured date of satellite S1 is shown in Figure 9 and Figure 10. The error calculation method is to calculate the differences between the measured date and the predicted date frame by frame. And differences value is defined as absolute error, which can reflect the real-time tracking ability of the predicted date to the measured date, where the day 1 prediction error is approximately 0.78 that exceeds the expected result. The correction coefficient is calculated K, and the coefficient K is introduced into the calculation of day 2. The absolute error of day 2 is less than 0.5a. That is in line with the expectation. An analysis of the error between prediction date and measured date of satellite S2 is shown in Figure 11 and 14. In Figure 11, Figure 12, and Figure 14, the error exceeds 0.7a means satellites are part OAS. It's out of ground process. After the satellite is completely out of the ground, the predicted date can track the actual date change well. The error can be controlled at about 0.5a. The energy supply of satellite solar array is mainly concentrated in the light region. We need to pay more attention to the output current prediction of satellite in the sun illumination region. The process of entering or leaving the ground shadow. The output of solar cell array has little effect on satellite energy, cannot be considered in prediction analysis. After 1 year extrapolation, the predicted current can be basically consistent with the actual measured value on the statistical characteristics such as mean, median, maximum, and so on. Mean error of S1 is less than 0.2a. Mean error is less than 0.2a. Maximum error is less than 0.4a. Mean error of S2 is less than 0.4a. Median error is less than 0.3a. Maximum error is less than 0.5a. In the above statistical characteristic, the mean value reflects the stability part of the output of the satellite solar cell array, which is generally the output state of the solar cell array after the Earth shadow is basically consistent. The working point is stable, and the Earth's albedo influence is small. The median value describes the central position date characteristics of the battery array output current date, reflecting the centralized trend of the date. The small mean error can indicate that the prediction is in good agreement with
Good morning, everyone. First, please allow me to introduce myself briefly. I'm Na Fu, now working as an engineer in the State Laboratory of Astronautic Dynamics, which belongs to Xi'an Satellite Control Center. It's my great honor to get this opportunity for this cyber presentation. For the next 20 minutes, I will give a short talk on mission planning of low Earth orbit debris collecting, which is entitled Multi-Debris Removal in Low Earth Orbit, based on swarm intelligence research on optimal guidance methods. There are 4 main sections to this topic: the motivation, the two-stage solving strategies, and finally the results and conclusions. As you remember, space debris raises an increasing threat to operational orbits and human missions. According to Kessler, the debris density at the low Earth orbit has already reached a critical state to create a cascading effect, which may result in an exponential increase of debris, even if no further launches will be made. In order to stabilize the debris population, we may have to actively clean space from orbital junk in the near future. Obviously, the best economy will be achieved when a number of well-chosen debris can be removed in a single mission, which we call it one-to-many removal strategy. The active removal mission, shorted for ADR mission, starts when an orbital transfer vehicle is released on the same position as the first debris to be removed. The cost and the duration consumed to remove the first target are therefore not included. After a deorbit kit has been attached to the debris, it's responsible for the debris removal. The orbital transfer vehicle then moves and waits the favorable opportunity to rendezvous with the next debris. The ADR mission is considered as finished if the reserved fuel is exhausted. All the last selected debris has been removed. In order to make low Earth orbit belt safer, the current paper focuses on the selection of the most dangerous debris in debris claws for removal, and guidance to the selected ones using chemical propulsion. With respect to fuel expenditure and overall mission time, the multiple rendezvous maneuvers need to be designed optimally so that the cost of the mission is minimized in a given time. It's clear that the design of such a space mission at a preliminary stage leads to a complex embedded optimization problem, as it mixes a vast combinatorial part as well as a high-dimensional continuous part. The combinatorial optimization problem is typically related to choose and order the debris among a population, while the continuous part aims to design the few optimal spacecraft rendezvous trajectories. The continuous choices obviously affect the search in the combinatorial part of the space. The considered problem can be formulated as a graph problem. In terms of graph optimization, the debris are the nodes, the transfer trajectories are the edges, while the successive missions are presented as open-ended subpaths. A major issue in this problem lies in the valuation of the edges. Each edge represents the orbital transfer between a debris and the next one on the path. The edge valuation is propellant required to perform the orbital transfer. Finding this minimal fuel trajectory is a challenging optimal control problem. It's out of reach to solve a global optimization problem in a direct manner. Thus, a two-stage procedure has been proposed to deal with it. More precisely, the two-stage process is split into two successive stages. First, a global search is performed to obtain the optimal removal sequence. Second, all transfer logs in the selected optimal sequence are precisely optimized with a continuous meta-heuristic. I'd now like to move on to the combinatorial part. Ideally, the minimum fuel, minimum time trajectories between all debris pairs should be provided as the inputs for the removal sequence optimization problem. as there could be tens of thousands of possible combinations to consider, and the number of possible trajectories between two specific debris is infinite. Thus, trying to obtain all trajectories would be unpractical. A feasible option is to approximate the transfer cost of any debris pair in advance. The removal sequence is then optimized. The velocity increments required for an individual transfer consists of orbital plane change and in-plane change part. If sufficient number of revolutions is permitted during each transfer, the effect of freeze on velocity increments tends to disappear. In such a case, the delta V for in-plane transfer is much smaller than that for plane change due to the similar orbit shape. Accordingly, it's reasonable to assume that the debris can be rendezvoused for removal only when the required velocity increments for plane change is small. Hence, the favorable rendezvous dates is referred to the time when such a preferable situation occurs. The plane change velocity increments depends on both the inclination and the rate ascension difference between the vehicle and the debris. Since the inclination difference portion is a constant according to the dynamic model, therefore, the rate ascension of ascension node separation dominates the velocity increments for plane change. In other words, the minimal plane change velocity increments is founded by minimizing the rate ascension difference. To this end, a straightforward option is to take advantage of J2 effect to nullify the rate ascension difference. Obviously, the transfer duration can be obtained as shown in the slide. Based on the above approximation, the removal sequence optimization problem with favorable rendezvous dates can be formulated as a variant of the traveling salesman problem, which is NP-hard. In order to solve the above-mentioned combinatorial problem efficiently, an anticlinear optimization-based meta-heuristic algorithm is chosen. ACO takes inspiration from the following behavior of ant species. Ants are able to find the shortest path from their home to a food source over a period of time. Each ant constructs a solution iteratively, and its behavior is guided by pheromone and heuristic information. The construction graph for the sequence optimization problem is the static adiaramation graph, in which the nodes are debris and the edges are solution components. The main iterative procedure of ACO consists of 3 steps. As the first step, each ant builds a solution according to the transition rule. Then, a local search position is employed to improve every constructed solution. Finally, pheromone is updated. The iterative process terminates when a stopping condition is satisfied. Based on the obtained optimal removal sequence with favorable rendezvous dates, the trajectory optimization problem is divided into a series of minimum few multiple impulses trajectory optimization sub-problems corresponding individual transfers, with a trade-off between computation time and solution quality. Up to 4 impulses are considered for each transfer leg. Due to the J2 effect, an initial cosine arc should be included prior to the first impulse to obtain a decrease in transfer cost. The final impulse is used to match the vehicle velocity with the target debris velocity to complete the rendezvous. The complete maneuver strategy of a transfer leg is entirely determined by a set of 11 variables. To deal with the trajectory optimization problem of each transfer leg, a meta-heuristic which extends ACO to continuous domains is adopted. ACO for continuous domain follows the incremental construction characteristic of the ACO and unsample the problem-based continuous probability density function for each continuous variable. Then, unlike the ACO, modify the pheromone table based on the components of good solutions to keep a history of its search process implicitly. ACO for the continuous domain updates the solution archive as a way of maintaining an explicit memory of the search history. The debris cluster with inclination close to 82 dig is chosen for detailed analysis. The orbital elements of the 4 chosen debris are also shown in the slide. The optimal 3-leg transfer in terms of velocity increments is shown in this slide. Estimation and exact results are also compared in tables. As we can see in the table, estimation of rendezvous times is usually extremely accurate. Furthermore, trajectories of the spacecraft are also illustrated in the figures. We can easily know from the figures that most of the required change of rate ascension differences between the debris and the transfer vehicle is nullified with the effect of J2 perturbation, and only minor adjustments are obtained with the impulse instead. In this paper, we consider the planning for the multiple debris objects removal mission. A 2-stage procedure has been proposed to deal with it. Our result opens the possibility to build more efficient and reliable searches by anticollinear optimization on preliminary stage design for the debris removal mission. Well, that's about it for now. If you think of other questions, send me an email. At last, thank you all for your attention.
Hello everyone, my name is Du Xiaoqiang from Northwestern Polytechnic University. I'm honored to have this opportunity to give this speech here. Today, my topic is gear-tooth fault detection based on design convolutional neural networks. There are 5 parts in this study, including introduction, intelligent detection model, tooth fault detection strategy, data validation, and conclusions. Now, let's look at the first one. As we know, gearbox plays a vital role in model industry, such as aerospace, automobile, railway, and so on. And there are many different methods of the tooth fault detection. For example, Liang proposed a bundling and mapping strategy to interpret the vibration signal. Xue proposed a 20-degree of freedom planning theory, gear loop and parameter model. Yang proposed an auto-regressive model with exogenous variables. Liu proposed a fault detection model combining fast dynamic time warping and correlated kurtosis techniques. Well, all of them use artificial design features, which can bring many man-made efforts. Therefore, to improve these disadvantages, This paper proposed a same model to detect tooth fault. This is the proposed SAM model. As we can see, this model can be divided into three parts. First, data pre-processing stage, consisting of symbolization and one-hot encoding stage. Second, feature learning and classification based on CNN. And last, health condition will be given by the prediction score. For the symbolization stage, in this paper, equal probability symbolization is used to symbolize the vibration data. It can be concluded into 5 steps. First, time series. Second, the time series will be sorted by amplitude. Third, determine the number n of symbols. Fourth, calculate the n-1 threshold. And finally, calculate symbolic sequence. For the one-hot encoding step, one-hot encoding will assign different values of variables to an m-dimensional vector with only one bit of 0. As for SN, we use normal, convolutional layer, and polylayer to extract the features. For convolutional layer, it's mainly used to extract the abstract features using a series of filters. Pooling layer is often placed after the convolutional layer to reduce a large number of parameters and avoid overfitting further. For the output layer, this model is a binary problem. Therefore, we use a single mode function as the activation function for the output layer. Now, this is a part of tooth fault detection strategy. Tooth fault detection strategy can be divided into 2 parts. First, obtain the weight series for the input. Second, location the gear tooth fault. For the first one, there are 5 parts. First, 1 million random symbolic sequence will be the input of the trained model. Second, we can obtain 1,000 highest score sequence by the result. Third, calculate one-hot matrix of this sequence. And fourth, obtain the frequency matrix by arranging this matrix. Finally, obtain the weight series by extracting max value of each clue. For the second part, it consists of 3 steps. First, obtain the weight series by extracting mass value for each column. Second, calculate the weight of each tooth because the vibration signal is composed by the signal of each tooth. Third, the biggest weight is for the tooth. This is a part of data validation. The Gearford experiment were conducted on rotating machinery, which is shown figure 7. As we can see figure 7a, the machinery fault simulator system consists of motor, load, gearbox, and accelerator. For the figure 7b, it's the layout of the test ride. Moreover, there are some experiment descriptions. First, the sampling frequency was 12 and 800 Hz, and the rotating speed was 300 round per minute. Second, the proposed method is used for binary problem. Third, in the experiment, 2 conditions are introduced, including normal condition and mistooth condition. And this is the setting of the designed cell model. This is the setting of the simulation dataset and experiment dataset. For the simulation dataset, each fault type number is 2000, and the length of each sample is 512. The training rate is 0.8, and each condition has 1,600 samples to train and 400 samples to test. For the experiment dataset, each condition has 480 samples, and the length of each sample is 512. The length contains 2 paired for the vibration signal. The training rate is 0.8. The total number of training sample is 788, and the test number is 192. Figure 5 and Figure 8 give the samples of their vibration signal. These are the validation results. First, for the simulation data, we can easily find that which part of the input signal is more important. While for the experiment data, it's hard to find which part of the input signal is more important. Therefore, we take the second step of the detection strategy to locate the true spot. The result is given as a figure. We can find that the tooth 2 has the biggest weight, which means tooth 2 is a 4 tooth. What's more, the around teeth also take higher weight compared with other tooths. And finally, there are some conclusions. For conclusions, first, a designed structure is proposed by introducing symbolization and one-hot encoding, which can effectively identify different gear faults. Second, a detection strategy is proposed to locate the gear tooth fault failure. Third, the effectiveness of the proposed method is validated by the simulation data and the experiment signal. First, the detection result can give certain instruction for failure mechanism. For future work, it is the application of high-weight combination of weighted series. Thanks for your listening. Thank you.
Dear everyone, I'm Zhang Yingying from Harbin Institute of Technology. My topic today is Trajectory Design for 6DOF Asteroid-Powered Landing via Convex Optimization. Landing vehicle on asteroids to obtain high-resolution data and soil samples are becoming increasingly popular in recent years. It's an important way to understand the formation and the evolution of the small bodies and the origin of the solar system. In order to successfully complete the mission, the spacecraft must softly land it on the intended landing site with pinpoint precision. However, there are challenges arise from designing trajectory design, such as complicated nonlinear gravity with irregular asteroid shape, the small rotating bodies, and the low thrust of the vehicle, even with the infrequent and delayed communication from the ground. So it is necessary to propose a reliable powered landing trajectory design algorithm that can be rapidly computed on board. For the problem formulation, we consider the trajectory design problem as the optimal control problem, which is to get the vehicle from the initial state to the landing site. First, we give two reference coordinate frames. One is the asteroid fixed coordinate frame. Another is a vehicle fixed coordinate frame. First, we give the mass depletion. We assume the field of the vehicle depletes at a rate proportional to the magnitude of the thrust vector. So we can give the mass depletion in terms of the thrust. For the dynamics, we first express the translational motion of the vehicle in the asteroid fixed frame. The translational motion of the vehicle is 3DOF. While we express the rotational motion of the vehicle in the vehicle fixed coordinate frame, it is also 3DOF. So the dynamics for the vehicle is 6DOF. Besides, there should be state constraints to keep the safety of the vehicle. So we first give a glide slope constraint to avoid undesired collisions with the asteroid. While we also want the onboard camera can track the landing site during the landing process. Give the FOV angle of the camera bit, we can give a FOV constraint to keep the landing site always in the field of view of the camera. Besides, there are restrictions on the controllability, which are the constraints for the magnitude of the thrust and the torque. For the cost function, we consider two problems. One is non-convex continuous time free final time problem, which is also the time optimal optimization problem. Another is the non-convex continuous time two-point boundary problem, which is a film optimal optimization problem. Then, given the boundary conditions and combining the dynamics, the state constraints, and the control constraints, above all are the optimal control problem for the trajectory design. In the problem formulation, we make the trajectory design problem as the optimal control problem. In this section, we cast the original problem to be a convex optimization problem. The convex optimization has many advantages. It is well developed and can be solved with custom solvers. And the local optimal solution of the convex optimization is also the global optimization solution, and it can be applied in the time-crucial and real-time process for the onboard computing algorithm. We first define the state vector and the control vector. Then we do convexification of the original problems. The original problems are non-convex continuous time optimization problems. Because the nonlinear and non-convex dynamics, the non-convex FOV constraints, and the non-convex thrust constraints. Therefore, linearization is adopted to turn the original non-convex problem into convex problems. For the convexification for the field optimization problem, we can directly linearize the dynamics, the FOV constraints, the thrust constraints. While for the convexification for the time optimal problem, we first normalize the flight time interval into 0 to 1 interval and use the time dilation to cast the free final time problem to be fixed time problem. Then we linearize the normalized dynamics. While for the FO1 constraints and the control constraint, they share the same form of the linearized field optimal problem. Finally, the trajectory is given by successive convexification by solving a sequence of the related convex sum problem, and the sum problem in each iteration is solved by second-order co-programming. Since the convex optimization problem is also the continuous time problem, we do discretization for the convex optimization problem. It is to use the last solution as the reference trajectory. For the field optimization problem, we discrete the time domain 0 to Tf into n equal intervals with time increment delta t. And impose constraints on each temporal node. So we can give the discrete mass depletion, the discrete dynamics, the discrete state constraint, the discrete control constraint, and the discrete cost function. For the time optimal problem, we discrete the normalized time domain and impose constraints on each node. So we can give the different mass depletion and the different dynamics for the time optimal problem. While for the state constraints and the control constraint, they share the same form of the discrete film optimal problem. Then we can give two problems. One is convex discrete time optimal convex optimization sum problem, and another is convex discrete time film optimal convex optimization sum problem. In the two sum problems, virtual control and trust regions are used. They are used to eliminate the artificial infeasibility caused by the linearization of the dynamics and the state constraints and the control constraint, which can guarantee the linearization can capture the non-linearity of the original problems and keep the problems remain bounded. The aim of the paper is to find a film optimal trajectory in the optimal flight time. So we combine the film optimal optimization problem and the time optimal optimization problem, which is making the obtained time optimal trajectory as the initial reference trajectory, and making the flight time equals to the time domain using the initial reference trajectory and the flight time. We can give the final trajectory, which is the final film optimal trajectory, achieved by solving the convex discrete time film optimal convex optimization sum problem. Then we give some simulation results. The simulation is done by landing on asteroid Cascade, and the polyhedron gravitation method is adopted to calculate the asteroid gravity, giving a maximum iteration number and acceptable state trajectory deviation. When the iteration number and the state trajectory deviation are more than the given values, the iteration stops. The simulation results are given in the features. In the features, the green lines are the results of the field optimal in using the solution of the time optimal optimization problem, while the red lines are the results of the time optimal single. As can be seen from the features, the field optimal optimization will use few field and the trajectory is more smooth compared to the time optimal optimization, while the simulation results shows that the trajectory design algorithm combining the time optimal and the field optimal optimization problems solved by the successful convexification is feasible and reliable. So above all is my topic. Thank you very much.
Hello everyone. Today the title of the paper I want to report is Anomaly Detection Method based on Granger Causality modeling. Satellites are very expensive to manufacture and require high reliability. Monitoring a large amount of telemetry data during a satellite orbit operation. The telemetry data are an important data source for analyzing the intercollision of the satellite system and detecting anomalies. Telemetry data is in the form of time series, and there may be mutual influence and correlation between these time series. Due to the diversity of its influence and association forms, it is necessary to establish an effective model to determine the association relationship between them in order to detect anomalies on this basis and identify the cause of anomalies. In this paper, we use Granger causality model to analyze correlation between time series of telemetry data and establish a causality model, detecting anomalies according to the causality which under normal circumstances and find out the cause of the anomalies. The case study shows that our method is effective. I will explain our proposed method from these four aspects, namely introduction, method, case study, and conclusion. The first part is introduction. There has been a lot of work on association analysis of time series. There are three kinds of methods for analyzing correlation of time series. The first one is correlation coefficient. The second one is influence structure diagram. The third one is some statistical models. As to correlation coefficient, for example, Pearson correlation coefficient and Spearman correlation coefficient. But when the time series have different change patterns, or the correlation has a lag relationship, these methods cannot reflect the correlation well. Number two is by extracting relevant features of time series and then calculating the correlation coefficient. But when the time series is very long, it may be difficult to give the fluctuation relationship of the time series accurately. The third one is for time series of the same length. Move to calculate the correlation coefficient to determine whether they have a lag correlation and find out the lag time. The second one, influence structure diagram. Try to find out the influence structure diagram when the time series is abnormal, and find the influence relationship between the time series. The time series anomaly is calculated by the skewness of the data in a sliding window relative to the distribution of the entire time series. But cannot recognize anomalies caused by some historical data and some statistical models. There are many statistical models used to calculate the relevance of time series, like VARMA. Some researchers use Granger causality models for anomaly detection, like a graphic model, Granger-Lasso algorithm, and anomaly. Granger causality for time series anomaly detection. A graphic model to study Granger causality in multivariate time series is proposed to detect anomalies. The model calculates a relevant anomaly score for each variable through the Granger graphic model, which can provide information about the possible causes of anomalies. Dependency anomaly detection for heterogeneous time series, a Granger-Lasso approach proposed an improved Granger-Lasso algorithm, which is applicable to a wide range of heterogeneous time series. Statistical causality analysis of InfoSeq alert data. The use of Granger causality test for anomaly causation is applicable to anomalies based on anomalies, but there is no analysis method for the cause of anomalies. In general, much work has been done on time series anomaly detection, but it is still faces many challenges, including the influence relationship of time series is diverse, and it may be related in trend, shape, or pattern. At present, there is lack of more general models and methods to accurately determine the relevance of time series. The second is for anomaly detection based on telemetry data. Due to the huge amount of data, the current real-time nature of many anomaly detection methods is difficult to meet the requirements. This paper proposed a method of time series association analysis and anomaly detection based on Granger causality model. The main work is as follows. Number one is use the Granger causality model to discover when there is a correlation between time series. This correlation is diverse, including trend correlation, time correlation, pattern correlation, and so on. The second is include the Granger causality model to reduce the time complexity of the calculation so that it can quickly produce results for large amounts of data. The third is quickly find out the case of anomaly based on the Granger causality model. Next, we can see one method for anomaly detection. We use Granger causality model to detect anomalies. Granger proposed the Granger causality model in 1969 to analyze the correlation between economical variables. After years of developments, Granger causality models has been applied to many other fields, and many improved methods have been proposed. Given two time series X and Y as T is the length of the time series. There are 6 steps for Granger causality model. The first step is verify this X is the Granger causality of Y change. The test requires the estimation of the following regression models: the second equation and the first equation and the second equation. The two-step propose the null hypothesis of the test, that is, X is not the Granger cause of the change of Y. Then we should calculate the sum of squared residuals of equation 1 and equation 2, RSSU and RSSR. Next, construct F statistical. N is the sample for sizes. The details of F statistics we can see the equation 3. Test the fifth step is test null hypothesis. If F is larger than F alpha, then means beta 1 and beta q are not significant 0, then the null hypothesis should be rejected. That is, X has an effect of Y. Otherwise, the null hypothesis is accepted. That is, X has no effect on Y. The last step is swap the positions of F of X and Y, and test with Y is the Granger cause of the change of X in the same way. There are four cases of the Granger causality. The first case is X is the Granger cause of the change of Y, but Y is not the Granger cause of the change of X. We can say that X has an unilateral effect on Y. The second case is Y is the Granger cause of the change X, but X is not the Granger cause of the change of Y. But X is not the Granger cause of the change of Y. The third case is X is the Granger cause of the change of Y, and Y is also the Granger cause of the change of X. We can say that X and Y are related to each other. The first case is X is not the Granger cause of the change of Y, and Y is also not the Granger cause of the change of X. We can say that X and Y are independent of each other, and there is no influence relationship. If the past information of variables X and Y is included, the prediction effect of variable Y is better than the prediction effect of Y by past information of Y alone. That is, variable X helps to explain the future change of variable Y. It is considered that the variable X has an influence on the variable Y. The Granger correlation model relies on the variance of the best least squares prediction. Using all the information at a certain point, certain points in the past where the X and Y are trend correlations, shape correlations, or pattern correlations, all can be verified by Granger causality test. If there is a correlation between time series, then when they are in a normal state, if conduct Granger causality test, the result of the test is a case-free. That is, the two variables affect each other. For real-time monitoring, these variables are monitored in real time through a sliding window. Once it is found that the time series are not related to each other, an abnormality can be detected. Then use the processed data to test Granger causality, taking a sliding window of length t to detect time series that have been determined to influence mutually. By moving the window, conduct Granger causality test on each pair of time series of length t. Once it is found that the result of the test is not the case-free, that is, if there is no relationship that affects each other, an abnormality occurs and an anomaly is immediately issued to further determine the cause of the abnormality. When the Granger causality model test is carried out through the sliding window and an abnormality is found, the cause of the abnormality is determined by analyzing the test results. If the test result is case 1, X has impact of Y, but Y has no impact of X, we can judge that X is abnormal, because at this time X appears a fluctuation different from the normal state, and the state of Y is still the same as in the normal state. If the test result is case 2, Y has the impact on X, but X has no impact on Y. We can judge that Y is abnormal, because at this time Y has fluctuated different from the normal state, and the state of X is still the same as in the normal state. If it is the case 4, further discussion is needed, which is the content of our future research. We can see our case study. In order to verify the effectiveness of the method in this paper, two sets of related time series XE and X1 and X2 are taken. By conducting Granger causality test for X1 and X2, results shows that X1 and X2 have a mutually influential relationship, which is very consistent with the actual situation, which can explain that the Granger causality model is effective in judging the correlation of time series. When X1 and or X2 is abnormal, take a sequence of data and use sliding window to detect anomalies. When we move the sliding window, the result of Granger causality test during the abnormal time is no longer the mutually influential relationship between X1 and X2. The result matches the true situation. It can be concluded that even in the case of a large amount of data. The method in this paper can detect anomalies in time. In order to verify whether the cause of the abnormality can be detected, first take the time series of x1 is abnormal but x2 is normal, and the result of the Granger causality test are shown in Table 1. It can be concluded that the result of the test is that x1 has an effect on x2, but x2 has no effect on x1, and it is judged that x1 is the cause of exception, which is in line with the actual situation. We can select the table 1 is there. In order to verify whether the cause of the abnormality can be detected, first take the time series of x1 is abnormal but x2 is normal, and the results of Granger causality test are shown in Table 1. It can be concluded that the result of the test is that x1 has an effect on x2, but x2 has no effect on x1, and it is judged that x1 is the cause of exception, which is in line with the actual situation. Similarly, then take the time series where x2 is abnormal but x1 is normal, and the result is shown in Table 2. It can be seen that the result of the test is that x2 has an effect on x1, but x1 has no effect on x2, and we can judge that x2 has an abnormality, which is in line with the actual situation. It follows from this that the method in this paper is effective in determining the cause of the anomalies. Then we can conclude our paper. This paper attempts to use Granger causality model to determine whether the time series are correlated based on the found relationship to monitor in real time, find anomalies in time, and further determine which variable caused the anomaly. When an anomaly occurs, the case study shows that the proposed method in this paper is effective. In future work, we will further study how the related variables affect each other, as well as the analysis of the influence of one variable on other related variables when abnormal. That's all. Thank you.
I'm so honored to be with you to communicate academic questions and ideas. The title of my academic presentation is A Review of Fault Detection and Diagnosis of Satellite Power Subsystem. I shall only take 15 minutes. First of all, I want to introduce myself. I'm Wei Huajing, coming from Harbin Institute of Technology, China. The content is listed as follows. In recent years, there has been a climax of satellite launch in the world. In 2019 alone, 103 launches have been carried out worldwide, with a total of 405 payloads on board. Among them, China carried out 34 launches, becoming the country with the largest numbers of launches in the world. So far, China is operating more than 300 satellites. Satellite power subsystem plays an extremely important role in all subsystems. The failure of it often leads to disastrous consequences. According to historical data statistics, the ratio of on-bit failure of power subsystems is the highest. The state of it will also affect and constrain the functional behavior of other subsystems, thus directly affect the mission capability of the satellite. Next part, I want to talk about the fault detection of satellite power subsystem. Fault detection algorithms are divided into 4 categories: statistical methods, nearest neighbor rule, clustering, and deep learning. The principle of fault detection technology based on statistics is that the normal data appears in the high probability region of a random model, while the anomaly occurs in low probability region. This method uses normal data to train a statistical model and then use it to test samples. When the probability value of the detected sample belongs to it is relatively low, the sample can be judged as abnormal. Both parametric and non-parametric estimation methods can estimate the parameters of the stochastic models. The parametric estimation assumes that the normal data is generated by a parameter distribution. When the abnormal evaluation score of the test sample does not meet the probability density function, it can be determined that the sample is abnormal. In non-parametric estimation, the basic distribution is not assumed, and the information of the random sampling itself is mainly used to judge the quality of estimators. The maximum score estimator method is a non-parametric estimator method. Using non-parametric statistical model for fault detection, the model structure is not defined by prior knowledge, but determined by the given date. The principle of fault detection technology based on the nearest neighbor rule is that the normal data is distributed in the dense neighborhood, while the abnormal data is far away from it. The nearest neighbor rule needs a reasonable distance of similarity to calculate the distance between different samples. Euclidean distance is the most commonly used method. Based on the nearest neighbor rule, fault detection technology can be roughly divided into 2 categories according to the calculation method of anomaly score. One is to take the distance from the sample to the case adjacent center as the anomaly score. The other is to calculate the relative density to each sample as the abnormal score. K-nearest neighbor algorithm is a relatively mature algorithm. This method assumes that in the feature space, if most of the k-nearest samples near a sample belong to a certain category, then the sample also belongs to this category. Using this principle, we can distinguish the abnormal point from the normal point. Density-based density-based fault detection technology estimates the density of each sample neighborhood. A sample in low-density cluster may be abnormal if the sample in high-density cluster is normal. There are many similarities between fault detection based on clustering and the nearest neighbor rule. For example, they all need a distance measurement, and the choice of distance measurement method has a great impact on the results. The most difference between these two types of technology is that the distance considered by clustering technology is the distance between each sample and its cluster center, while the distance from each sample point to its nearest neighbor is considered by technology based on the nearest neighbor rule. The fault detection technology based on clustering can determine whether a sample is abnormal in three cases. First, normal samples are located in cluster center while abnormal samples are far away from any cluster center. Second, normal samples are located in large and dense clusters, while abnormal samples are located in small and sparse clusters. Third, normal samples are close to the nearest cluster center, while abnormal samples are far away from the nearest cluster center. The common clustering algorithm is k-means clustering. Deep learning can extract high-level features of data. Using this feature, normal data distribution can be obtained by training normal data. When the sample does not belong to this distribution, it can be judged as abnormal. The common use deep learning models for fault detection are LSTM and autoencoder. The LSTM natural network is a special type of cyclic natural network, in which gate is added to each cyclic body to control the flow of information. The three gates are forgetting gate, input gate, and output gate. The forgetting gate determines what information will discard from the LS unit. The input one determines how much new information we will add to the state of the LS unit, and the output one determines what information we will output. This makes LSTM not only have the advantage of dynamic memory of cyclic neural network, but also have stronger adaptability in time series data and analysis, and can extract features from non-stationary parameters. This characteristic makes LSTM outstanding in recognition and prediction. Autoencoder is a neural network with the same input and learning objectives. It can learn efficient representation of input data through unsupervised learning. Generally, autoencoder consists of encoder and decoder. The decoder transforms the input data into a fixed-length high-level feature, which is generally much smaller than the input dimensions. The high-level feature is used as the input of decoder to reconstruct the input sequence. Therefore, autoencoder can learn meaningful information to fully explain the characteristics of data. From encoder input sequence-to-sequence model, this kind of model can detect a fault by reconstructing the oral sequence and compare the reconstruction result with the oral input to find out the abnormal information. Next part, I want to talk about the fault diagnosis methods. Fault diagnosis those methods can be divided into knowledge-based methods, model-based methods, and data-driven methods. The fault diagnosis methods based on expert system construct a knowledge base about the target object by inheriting the knowledge and experience of the experts. The knowledge base is composed of abstract if-then rules. In addition to the knowledge base, each expert system has an important part of inference engine. According to some abnormal phenomena of fault validate, the inference engine codes the knowledge in the knowledge base and determine the fault step by step according to the inference steps. Quantitative model-based methods, also known as an analytical model-based method, is the earliest and the most in-depth and most mature method of fault diagnosis. This kind of method make full use of the knowledge of the system structure, behavior, and function to carry out reasoning diagnosis of the system. According to the different ways of generating residuals, model-based methods is divided into seed estimation method, equivalent space method, and parameter estimation method. Euclid transform can solve many problems that are difficult to be solved by using Fourier transform. So it is considered as a breakthrough development of Fourier analysis method. Compared with Fourier transform and window Fourier transform, it is a local transform of time and frequency. So it can extract information from the signal effectively and perform multi-scale analysis on the function of signals through the operation functions of scaling and translation. Support vector machine has many unique advantages in solving small samples, nonlinear and high-dimensional pattern recognition, and can be extended to other machine learning problems. The support vector machine method is based on the VC dimension theory and the principle of structural risk minimization. According to the limited sample information, it seeks the best compromise between the complexity of the model and the learning ability in order to obtain the best generalization ability. The last part is some discussion. In the past decades, for the detection and diagnosis, technology has developed rapidly. Especially the model-based photo diagnosis technology has made great progress. We have a wide range of applications in spacecraft photo detection and diagnosis. But there are still many problems to be further studied and solved. With the rapid development of artificial intelligence, how to use this new technology to photo detection and diagnosis, many people have made different attempts. But there are free applications in practice, which need further research and application. That's all, thanks.
Dear attendees, I'm Feng Xiaoen, the speaker of the application of population-based incremental learning algorithm in satellite mission planning. Today, I'm very honored here to behalf of our team to introduce the research works to you, and the main contents include 5 sections. Section 1 is Introduction. With the development of space technology and the popularity of satellite applications, the number and types of satellites are increasing, and they are playing a quite important role in fields of economy, military, and people's livelihood. Facing the growing demanding for satellite missions of users from all walks of life, satellite mission planning has become a hot research issue at home and abroad. We know that satellite mission planning refers to the process that the control department allocates satellite resources and satisfies various constraints to maximize the benefits of satellite missions. Obviously, it is quite sophisticated problem that is known as NP-hard problem, and the most difficult part is to find a method to solve it. And there are many researchers did this work. Most of the researchers use heuristic method to solve the problem, many including table search, genetic algorithm, and so on. But for complex large-scale satellite mission planning problem, there are still some questions like inadequate consideration of the constraints of the model, and the computational complexity and speed of the algorithm need to be improved. So, it is important to establish a reasonable mathematical model of satellite mission planning and propose an effective method to solve it. These are actually what we did in our paper, and it is worthy to notice that we proposed the PBIL algorithm based on real coding for solving this problem, which is different from the traditional binaural coding method, and we have verified the algorithm by some experiments. And now I will introduce the main works to you. Firstly, we establish the model of satellite mission planning and give the mathematics statement. The problem can be described as M satellites observe R targets in a planning circle and find the optimal mission sequence. For one satellite, the distribution result can be expressed like this, a 6-element array. And we made some basic assumptions to simplify the problem. The first is the target is regional, and the observation of the target by satellite requires a certain scaling time, that is, the observation has a certain duration. The second is each satellite carries only one remote sensor. And the third is the satellite need to maintain a stable attitude during the execution of the mission. After completing the former mission, it needs some time to adjust the posture. And we put some constraints in the model. Includes task time constraints, data storage constraints, and energy constraints. Then we put forward objective function. The optimization goal is to maximize the benefits, and we put forward the formula like this. After build the model, we come to the most important part, that is the method. We use the PBIL algorithm to solve the satellite mission planning problem. The key point of the algorithm is the real coding method and the update of the probability matrix. So I will introduce the encoding and venue probability in details later. And the other parts is no difference with the common PBIL algorithm. The fitness configuration is directly using the objective function that I introduced in the model just now, and the end condition is the number of evolutions determined by some numerical experiments. Now I will explain the encoding part. When using the traditional PBIL algorithm for satellite mission planning, binary coding is often used like this. Each byte of the chromosome is a time window, and its value is 0 or 1. That indicates whether the window is selected. That means if put the 1, the window is selected, but if you put the 0, the window is not selected. The length of the chromosome is the number of visible time windows for all satellites towards all targets. However, in the actual satellite mission planning process, the number of satellites and targets will be large, and the number of visible time window will be larger. So, if use the binary coding method, the chromosome will be so long, and it will take a long time for each byte to check the constraints, which will result in very low efficiency. So, to improve the efficiency of the algorithm, we propose a real number encoding method. Like this, each byte of the chromosome now represents a target, not a time window. For example, target I, it means the ith byte of the chromosome. Ni is the total number of time windows for the target I, and each window is numbered from 1 to Ni. This means that the value of the ith byte of the chromosome has Ni selections. To notice that if we use the binary coding, the selection is only two, that is 0 or 1. But in the real coding, we have Ni selections. This is the difference. In the real coding PBIL algorithm, the probability is a matrix. Like this. This is a matrix. The initial probability matrix is shown like this. Ensure that the value of each gene bit has the same probability at the beginning, because at the beginning we don't know to choose which window. Everyone has the same value. But when the evolution is going, we will update the probability matrix. And among the newly generated populations of each generation, the individual with the highest fitness value is selected for learning. And that means the higher fitness value is, the higher probability is. And the probability matrix is updated. Please remember to normalize the matrix to keep the sum of the probabilities to be always 1. So there are the algorithms steps. Step 1 is to encode and initialize. Step 2, then we go to step 2. Step 2 is using the probability matrix to guide the generation of the new population. Then we go to step 3. Step 3 is to check the constraints. If the mission does not pass the conflict check, it will be abandoned. That means the value will be 0. Then we go to step 4. Step 4 is to calculate the fitness value of each individual and get the best individual with the highest fitness value. That means we find the best individuals that guide to we get the evolution direction. Then we go to step 5. Step 5 we have two choices. If the end condition is satisfied, we shift to step 6. That's the end of the algorithm. But otherwise, if we will update and normalize the probability matrix with the best individual, and we return to step 2 and then go to forward step 3, 4, 5, and then we make a determination about to shift to 6 or shift to step 2. But in the end, we come to the step 6 and get the mission planning scheme sequence. In this section, we have some experiments to verify the model and the algorithm. We set the simulation scenario in STK. The number of satellites is selected to 10, and this is the distribution of the satellites in STK. The targets are randomly established in global and assigned to each target a benefit value, and this is a distribution. And then the data when we set the ground stations. We set 12 ground stations. This is the distribution of the ground stations in STK. Then we get the results. As shown in the table and the picture, it can be seen that PBIL algorithm can effectively solve the satellite mission planning problem. As the evolution curve shows, it coverages around 80 generations and has a high computational efficiency. In order to learn more about the algorithm performance, we have done some comparison experiments of genetic algorithm and PBIL algorithm for solving the same satellite mission planning. The evolution curves of PBIL and JA like this. From the result, we could know that under the same condition, the PBIL algorithm coverages rapidly around 18 iterations, while the generation of genetic algorithm coverages after 100 iterations, and the running time of PBIL is much shorter. In this table, we can see that it's about double times. GA's running time is about double times to PBIL's running time. And this indicates that PBIL algorithm has faster computational performance, and the evolution curve of PBIO has smaller fluctuation. That means PBIO is more stable. So in terms of the computational efficiency, optimization quality, and algorithm stability, we can know that the PBIO has a better performance to the genetic algorithm in solving the same problem. So, with the research works, we can draw some conclusions. First of all, we analyzed the constraints of satellite operation and established the mathematical model of satellite mission planning. Secondly, we proposed the PBIO algorithm based on real coding for solving satellite mission planning, which is different from the traditional binaural coding method, and we verified the flexibility and effectiveness of the algorithm by some experiments. In addition, we compared the performance of PBIO algorithm with genetic algorithm for the same satellite mission planning scenario, and the PBIO shows a better performance. So, this is the end of the presentation. Thanks for your watching and listening.
Hello, dear professors. My name is Sun Peng. Next, I will report my paper, Research on Satellite Fault Detection Method based on MSET and SRPRT. The authors of this paper is me and my tutor, Jing Guang, and we all come from National University of Defense Technology in China, Hunan Province. My report has 4 parts: Introduction, MSET, SRPRT, and Example. First of all, Introduction. Since the beginning of 21st century, the increasing requirements of mankind for spacecraft technology have forced it to become more and more complex and increase investment. Our research object is satellite fault detection. There are three common methods. First is regression tree, but it is difficult to prove because of overfitting tendency. Secondly, machine learning. Its disadvantage is a lot of historical data is needed. Last of all, Bayes network. The disadvantage is the premise is that the distribution is independent. All above methods do not involve satellite fault monitoring under multi-parameter conditions. In this paper, a model combining multiple state estimation with sequential rank sum probability retail test is proposed for that. Next part is MSET. MSET steps has 5 steps. Step 1. Collect new observation metrics based on actual telemetry data. And step 2. Select training data. The training data needs to include all health states of all monitoring parameters under the normal operating state of the system. The normal operating state of the system here includes not only the steady change state of the monitoring parameters, but also the normal degradation state. And then step 3. Construct mirror matrix and generate recensional training data. And step 4. Calculate healthy residuals. When calculating the healthy residual, MSET is performed in 2 steps: calculating the estimated value of all remaining training data and calculating the health residual between the estimated value and the remaining training data. At last, step 5. Calculate actual residuals. When calculating the actual residuals, MSET is also performed in 2 steps: calculating the estimation matrix of the observation matrix and calculating the actual residual between the estimated value and the observation matrix. Next, the memory matrix generation method. Step 1. Number of states L determined manually. Step 2. Select the extreme state of each monitoring parameter included in the training data. And step 3. If the number of selected extreme states is less than number of memory matrix states, the extreme state is added to the memory matrix. Then calculate the vector of incline norm of other date in the training date. After sorting, equidistant sampling is added to the memory matrix to complete the construction of the memory matrix. Then part 3, SRPRT. SRPRT steps is almost 6. Step 1. Build statistical assumptions. Step 2. De-averaging. Step 3. Sort by absolute value. Step 4. Remove zero value and reorder. Step 5. Calculate Wilcoxon signed rank sum statistics by sample size. And at last, set threshold for fault diagnosis. The details is shown in my paper. In order to verify the effectiveness and accuracy of the SRPRT, a control experiment was designed according to the following method. The parameter M corresponds to the mean deviation of the fault data in the hypothesis from the normal data. The data used in the experiment are random data that follow the normal distribution with a mean value of 0 and a variance of 1. Therefore, the result of our algorithm determining a failure is false alarm. The parameter FAR observation value is the number of false alarms divided by the total of samples. The test method is to observe the false alarm rate as small as possible. Experiment 1. Verify the effect of the parameter M, indicating the degree of mean shift on the experimental resource. Set MAR is 0.1 and FAR is 0.003. The number of samples is 1 million, and observe the change log of FAR observation value with M. As shown in the above figure, the FAR observation value decreases with the increase of the mean value M of the abnormal data offset. The larger M is, the higher the data is judged as failure criterion, and the more difficult it is for the sample data to be judged as failure, which conforms to the original design assumption. M can be used as a confidence index to join the algorithm using process, which is convenient for adjusting the accuracy of the algorithm. And then in this paper, M is taken as 0.8. Experiment 2. Adjust the parameters and find the optimal MAR and FAR parameters. Change the MAR and FAR values and conduct multiple experiments to find the MAR and FAR corresponding to the smallest difference between the actual failure rate and the theoretical failure rate. Set the failure rate and add abnormal data to the normal data in proportion to the failure rate. Normal data and abnormal data run SRPRT algorithm separately. After the algorithm runs, the observed FAR is the number of abnormalities in normal data divided by the total number of normal data, and the observed MAR is the number of normalities in abnormal data divided by the total number of abnormal data. As shown in figure, the x-axis and the y-axis respectively represent the theoretical values of MAR and FAR, and the axis represents the absolute value of the difference between the actual measured value of the failure rate and the theoretical value of the failure rate. Therefore, the curved surface is similar to the parabolic surface, and the lower model zone is the zone with the smallest failure rate error. When the measured failure rate is closest to the failure rate, the lowest point in the figure. The corresponding MAR and FAR are selected as the optimal parameters. And we can see the lowest point takes MAR is 0.015 and FAR is 0.02, and the value of Z at this term is smallest. So the algorithm selects the optimal parameters 0.015 and 0.02 in line with the experimental results. And the last part, example. The experiment case selects satellite attitude control system for fault detection. Compare the advantages and disadvantages of the exciting MSET combined with SPRT and MSET with SRPRT. All data are normal data, and the total sample data is 1 million, with a total of 19 parameters. According to the alphabetical order of the English names, the parameters follow the normal distribution with mean values of 0, 1, 2, 3 to 18, and variance of 1. Since the mean value of the residuals after MSET calculation of 19 parameters is not 0, the mean value of variance needs to be shifted. For the SRPRT algorithm, the parameters M is equal to 0.5, 0.8, and 1.5, and the MAR is equal to 0.015 are set in the experiment. Since the FAR and FAR observation values are both small, in order to better display the relationship, the horizontal coordinate takes the logarithmic function of FAR to lengthen the distance between the horizontal coordinates. As shown in figure, MSET with SPRT under the condition of FAR M are not good as SRPRT. When M is unchanged, the FAR increases and the FAR observation of SPRT and SRPRT increase. However, when the FAR is greater than 0.001, the FAR observations of the SPRT increase significantly and are much larger than the FAR observations of SRPRT. Generally speaking, the SRPRT false alarm rate is greater than the SRPRT when M is unchanged, and the growth rate is extremely fast, which is obviously inferior to the SRPRT. When FAR is unchanged, M increases and the FAR fault detection values increase, which conforms to the algorithm design idea, and the SPRT performs well when M is equal to 1.5, although the observed false alarm rate of both algorithms is smaller than the theoretical false alarm rate. The SPRT false alarm rate is still much higher than the SRPRT false alarm rate. Therefore, it can be proved that the SPRT is effective but not as accurate as the SRPRT. It also proves the effectiveness and accuracy of the SRPRT algorithm from the side. Moreover, because SRPRT method requires sample to follow a prior distribution with unknown parameters, satellite minor data may not necessarily meet this requirement. However, the sample single required by the SRPRT method is continuous and systematical about the median or mean value, and the satellite minor data can be satisfied after adjustment, and the SRPRT algorithm has higher precision than the SRPRT algorithm. So in the paper, the non-parametric method SRPRT is selected as the method of fault material with the MSET method. The advantage of the algorithm in this paper is that it can be used for multiple parameter fault detection. The accuracy of the algorithm is significantly higher than the accuracy of combination of the MSET and the SRPRT. The disadvantage is that the running time of the algorithm is slightly longer than the SRPRT, and it still needs to be improved in the future. Our follow-up work will focus on comparing this algorithm with other fault detection algorithms such as regression trees, grid system theory, Bayes network, and machine learning in the performance of accuracy and operation efficiency, and to improve the weakness of the algorithm. Thanks for listening.
Hello everyone, thank you for coming to my presentation. Here, the title is Data-Driven Approach for Satellite Onboard Observation Task Planning Based on Ensemble Learning. Now, I will show my work from the following 5 parts. As shown in the figure, the satellite orbits the Earth. It decides whether to collect images when a ground target comes into its view. Satellite onboard observation task planning program is to build an optimal plan to perform the requested observation task in an efficient manner. In our program, the objective is to maximize the total profit. Satellite onboard observation task planning can enhance the responsiveness to changes of onboard conditions, such as the arrival of new observation tasks or unexpected energy or memory level, which has attracted considerable attention from researchers and space agencies. However, the limited computing resource on board and the uncertainty of observation requests bring greater challenges to the onboard task planning. In general, the approaches of satellite onboard task planning can be mainly classified into 2 categories. One is batch-based planning, and the other one is rolling planning. In the batch-based planning approach, the onboard planner must develop a new plan once the onboard condition changes. However, it has a significant time delay from when the planner is invoked to when the planner builds a new plan, that it is unresponsive to a quickly changing environment. In the continuous planning approach, any unexpected change in the horizon may trigger the planning process and use the heuristic methods to dynamically update the plan. However, designing a good heuristic method is very difficult, which makes it hard to find an optimal solution. To overcome these drawbacks, we proposed a data-driven onboard planning framework. It enables the satellite to decide the observation task to execute in real time using machine learning techniques. The framework consists of two parts: offline learning and online decision making. In offline learning part, each planning instance is scheduled by the optimization tools or methods. Then, the features and levels of each observation task is computed from the optimized plan. Then, a classifier is trained by supervised learning methods to learn the decision rules for judging whether an observation task can be arranged. In our work, the classifier is the Ensemble learning algorithm. Considering the limited computing power of the onboard computer, the offline learning part can be done on the ground. In the online decision-making part, the classifier is used to decide the observation task to perform next during the executing of the current one. It makes a decision on the observation task one by one. Based on this model, the satellite can decide the observation to execute in real time. When we use the Ensemble learning methods to make decisions on the observation tasks, the main problem we face is how to construct a fixed size length features to represent the tasks. So we designed 5 classes of features based on the empirical knowledge. They are state features, task features, local features, global features, and transmission features. State features represent the resource level, such as energy and memory. Task features represent the attributes of decision task. Local features represent the degree of conflict of the decision task with other observation tasks. Global features represent the distribution of the observation task, which can avoid the onboard player making short-sighted decisions. Transmission features represent the degree of competition between the decision task and other observation tasks on memory resource. Compared to the features, the computation of labels is much simpler. The labels of an observation task is 1 if it is in the optimized plan. Otherwise, its level is 0. Given the features and labels, we can train the classifier. We select the following 3 classical ensemble learning algorithms: random forest RF, GBTT, XGBoost. Given the proposed approach, now we will proceed to experiment. In the experiment, we randomly generated 5 sceneries. Each scenery contains 120 instances, so we totally have 600 planning instances. In these sceneries, the number of observation tasks is ranged from 100 to 500. The planning horizon is set as 24 hours. All experiments were run on a Windows 7 operation system. To verify the effectiveness of our method, we solved each instance by simplex in offline model and use it as the baseline. Another 2 online planning algorithms, profit first heuristic algorithm and dynamical profit system benefits heuristic algorithm, are used for comparison. To measure the performance of these algorithms, the following 4 statistics were computed: accuracy, response time, average profit gap. Here is the meaning. First, we test the effect of the 5 types of features on accuracy and profit gap. We see that accuracy increase and the profit gap decrease with the use of more types of feature. The reasonability of these 5 types of features is confirmed. It shows that they all play an important role. Next, we tested the impact of the top N features on profit gap based on their importance. We can see that the profit gap decreases as more features are selected. The profit gap is no longer significantly reduced when the number of features exceeds 16. So, the top 60 features are key features, and we choose them for next experiments. To further evaluate our problem, we compare it with 2 online algorithms. PF, GPSB. C is defined above. In the table, the average profit gap, and average time of 6 algorithms is shown. In the table, the profit gap of RF, GBDT, XG boost are far less than that of GPSB and PF. (3.5%, 3.5%, 5.5%, 8.2%, 9.8%. We can also see that the response time of GBDT and boost are less than 1 millisecond. In practice, the computing power of onboard computer is from 100 to 1000 times less than the computer we use. So, it's suited for the computation on board. We can see that the response time of PF, GPSB, GPDT, and boost are approximately the same. From the experiment, we can conclude that the experiment investigates the feasibility of our proposed method. From our work, we can make the following condition. Our proposed data-driven onboard planning framework combine ensemble learning technology can decide the observation task to execute in real time. The performance of the proposed approach is out of the rule-based heuristic method. In the future, we can use deep neural networks to automatically extract features and improve the accuracy of the decision-making model. Okay, thank you.
Hello everyone, it's my honor here to share some of our study with you. Analysis and strategy design for quantitative model-based fault diagnosis. It contains 4 parts. Introduction, Model-based fault diagnosis methods have been developed in two distinct and parallel research domains in the past few decades. One comes from automatic control, known as fault diagnosis, based on quantitative model. Another one comes from artificial intelligence, called qualitative model. They are all based on deep knowledge, but developed independently. Quantitative methods focus on diagnosis, saving process. They have certain significance for quantitative model-based methods. This paper studies the traditional qualitative method by combining system structure information and then provides a new fault diagnosis strategy. By this study, the fault diagnosis based on qualitative models is extended from single structure system to multiple structure system. The designed strategy can isolate the fault of actuator and sensor with a reduced number of quantitative models working at the same time. The main contributions of this paper are as follows. Traditional methods and the existing problems are analyzed. Object systems and quantitative methods are redefined. Their diagnosis serving process is studied. Quantitative model-based fault diagnosis strategy using redundancy of system structure is presented. Traditional method. The traditional qualitative method commonly concerns certain dynamic system. The object system is usually described by a set of differential equations in state space form. It's composed of actuator, sensor, and process. An actuator fault is malfunction on certain control input. A sensor fault is an abnormal variation in output measurement. Process faults are changes in the inner parameters of the system that can affect the system dynamics. Quantitative method is typically achieved by constructing quantitative model to detect the consistency between the computed output and the real output. There are two kinds of diagnosis approach. Using pre-assigned fault model can achieve fault estimation, and using fault-free model can detect unknown fault. Model-based methods usually generate a set of residues to fulfill the isolation task. According to the insensitive and sensitive relationship between residues and faults, there are two kinds of strategy. for residual generation. The dedicated residual site can detect simultaneous faults. However, it needs more degrees of freedom to design. The generalized residual site can only detect one single fault, but it has more freedom for achieving robustness against system uncertainty. Quantitative model-based for the diagnosis method has these difficulty issues. The accuracy of consistent detecting will be influenced by disturbance, noise, and uncertainty. A system is constituted by three main points: actuators, sensors, and process. It is hard to judge the real petty fault. The fault-free model is simple, but only fault detection can be achieved. Faulty model-based method can detect various faults, but it is hard to be constructed. Thus, effective combination of two strategies is worth discussing. Fault diagnosis structural strategy. We define that one object system diagnosed by quantitative model based for diagnosis method is composed of a set of components and a set of measurements. The object system can achieve the specific function and realize the corresponding dynamic response from input to output. It contains the input parts called actuators, the output part called sensor, and the dynamic response relationship between input and output, which is abstracted as process component. Measurements refers to the direct value about the system, including control input and the measurement output. The text of fault diagnosis is defined as determining whether a fault occurs in the system, which parts are faulty, and what kind of fault occur. Analytical redundancy relation is defined as a constraint deduced from system measurements, which is the basis for constructing quantitative model. A residue is defined as the difference between outputs of real system and model corresponding to ARR. ARR support is defined as a set of components involved in the ARR, and the corresponding parts are called support components. Fault diagnosis and isolation based on quantitative models can be described in detail by the concept of ARR support. Fault detection is defined as determining a certain subset of the support components set and one or more support components in the subject are faulty. Fault isolation is defined as determining a certain subset of the support component set and all support components in this subset are faulty. As fault diagnosis results come from a subset of support components, the component set determines the maximum diagnostic granularity. The fault symptom matrix is defined as the binary relation matrix between the ARR support component and ARR. If the S component is a support component of the GARR, thus the element Ji is denoted by 1, otherwise it is denoted by 0. The S column is the fault feature vector of the S components, and two components can be isolated if and only if their fault feature vectors are different. According to the following multi-input and multi-output dynamic system S1, the corresponding fault symptom matrix is constructed in table by the shrinkage of dedicated residual set and generalized residual set. ARR1 is constructed based on the constraint relationship between U1, 2, 3 and U1, 2. It is only be used to achieve fault detection. ARR2 to 4 are constructed by using generalized residual set. AR5 to 7 using dedicated residual set. According to fault symptom matrix, it is easy to isolate the actuator fault. However, sensors and process components have the same fault feature vector, which means that additional information is required to achieve fault isolation. It is often difficult to construct more ARR to complete fault isolation for all support components. It will be influenced by constraint conditions as well as specific distribution matrix of actuator and sensors. In addition, more analytic redundancy relation means more models be built and run in parallel, which will increase the burden of computation. The strength of ARR generation for model-based method is studied from the perspective of system hierarchy and subsystem division. Consider the following system as true. If a new sensor C can be used to measure the intermediate process variables, and system can transformed into a new form as follows. The original system can be divided into two subsystems. After adding the new measurement C, the matrix diagnostic granularity is changed from the original components to new components. Namely, addition of measurement point is the benefit to more accurate diagnosis result. Further expanding the system discussed above into a multi-input and multi-output system S3. Fault detection and isolation for S3 is to determine the fault components from all these support components. Based on subsystem 1 and 2, 6 ARRs can be constructed, and the corresponding fault symptom matrix is showed in table. ARR 1 and 2 is analytical redundancy relations constructed according to all of 6 components in subsystem 1 and 2. ARR 3, 4, and ARR 5, 6 are analytical redundancy relations constructed according to subsystem 1 and 2 by dedicated residual set or generalized residual set. According to the above fault symptom matrix, the corresponding fault features vectors can be easily abated. The final fault diagnosis result can be determined. However, 6 quantitative models can be constructed and run in parallel, and the calculation amount is large. Quantitative model-based fault diagnosis structure strategy achieves the fault diagnosis task in 2 stages. In the first stage, the model is designed respectively for each subsystem. It is a fault-free model designed based on normal system, and its analytical redundancy relation contains all support components corresponding to ARR1 and ARR2, and thus the diagnosis result can be abated. In the second stage, a set of models is designed respectively for each subsystem. This analytical redundancy relations contain different support components. It can be achieved by dedicated residual sets or generalized residual sets corresponding to ARR 3, 4, and ARR 5, 6. Thus, the further diagnosis result can be abated. Through the above analysis, fault diagnosis strategy is established in the following. First of all, the 2 models designed in the first stage run in parallel. If there is a fault in system, we will get preliminary detection results. Thus, a subset which contains possible faults components can be avoided. According to the above, detection results, fault isolation in the second stage is started. If detection result is the first stage, the models corresponding to AR 3-4 activity, the fault components can be isolated. And if the detection result is the second result, the models corresponding to AR 5-6 are activated, and the corresponding fault components can be isolated. It can be seen that by adopting the above diagnosis strategy, the final result is the same as 6 models run in parallel. However, detection and isolation fault components stamp by stamp. The numbers of models running in parallel at the same time is reduced, and the burden of computations is also reduced. We limit the discussion of fault diagnosis and isolation to fault-free model in the beginning. However, the strange proposed above is also suitable for predefined fault model. We can also use the strange for satellite attitude control system. A satellite attitude control system includes actuators, inertial sensors, and direction sensors. The typical structure of satellite attitude control system is as follows. Fault may occur in any part, and it is difficult to consider all-path diagnosis. According to the proposed structural isolation strange, in the first stage, 2 fault-free models are designed according to dynamics subsystem and kinetics subsystems. Fault detection, observer 1 is sensitive to all actuator and gyro faults. Fault detection, observer 2 is sensitive to all gyro and star sensor faults. In the second stage, a bank of fault-free models according to dynamics subsystems is designed, called Fault Isolation Observer 1. It is sensitive to the specific actuator fault, and a bank of predefined fault models according to kinetics subsystem is designed. It is called a Fault Isolation Observer 2. It is sensitive to the specific gyro fault. Thus, the complete fault isolation logic is as follows. Conclusion. In this paper, the traditional quantitative model-based fault diagnosis method is summarized and the difficulty is analyzed. Furthermore, qualitative model-based fault diagnosis methods are redefined and diagnosis solving problem is studied. Finally, quantitative model-based fault diagnosis structure strategy which can isolate the fault and the actuator and the sensor with reduced model is proposed, and the corresponding analysis is also presented. Thanks.
Hello everyone, my name is Jidong Li, and I am from Beijing Institute of Spacecraft System Engineering. The name of my paper is Satellite Telemetry Anomaly Detection based on Gradient Boosting Regression with Feature Selection. So the first part is production. Nowadays, there are so many satellites in the space, so the on-orbit satellite will generate a large number of telemetry data, which can reflect on-orbit healthy state. Anomaly detection of the telemetry data is important for the reliability and the security of satellites. So this is why we doing the anomaly detection. And with the development of AI and machine learning, data-driven methods are mainly used for anomaly detection nowadays, which includes one-class classification such as SVDD and one-class SVM, and statistical methods such as Gaussian mixture model, and prediction-based methods such as LSTM network prediction, and supervised multi-class classification. So for one-class classification and mixed Gaussian model, also it has strong universality, and it has poor interpretability and unable to locate the cause of the problem. Further, when an anomaly occurs, the prediction-based method cannot handle the unpredictable telemetry variables. Moreover, due to the influence of the conceptual drift, the prediction error will be accumulated gradually, affecting the accuracy of the anomaly detection. For supervised classification, it is necessary to rely on experts to provide labels. So this is why it's a lack of training data from the satellite. For the, we have no labels, so this method cannot be used. This paper uses a gradient boosting regression algorithm to automatically learn the nonlinear complex functional association model by a data-driven manner, which is self-adaptive to the change of telemetry association altering caused by the change of operating conditions. Also, a novel feature selection method, which combines feature importance scoring through gradient boosting regression model training process and recursively lowest score feature elimination, can automatically man telemetry variables with association through multiple iterations without domain knowledge. The method is characterized by high interpretability, high accuracy, and intelligence. The second part is problem description. Data-driven anomaly detection requires first preparing training dataset, usually the historical telemetry data of satellites in orbit. Then, an anomaly detection model is learned from the training dataset through a data-driven manner. Finally, the trained anomaly detection model is used for anomaly detection for new on-orbit telemetry data. So this is the telemetry dataset. It contains a lot of telemetry variables, and for each variables, it is a time sequence. So this xk and is the telemetry individual telemetry variable, and x1, xk1, xk2 until xkp is stand for different time step. So we want is to is association mining and training the regression model. Take x1 for example, we want to man its correlated variables. For example, it's x2 and x5. We then learn the health baseline model x function 1, and after we train this function, train this model, we use this model to prediction and for the anomaly detection. I mean, we can get the prediction one and the true one. And we compare these two, get the regression error. And this regression error is used for anomaly detection. When this error is big enough, it means anomaly happens. And when it's not big enough, that's fine, that's okay. The third part is anomaly detection algorithm. The first question is how to build the baseline model. So we used gradient boosting regression. So why we use the gradient boosting regression? Because this kind of ensemble models. Ensemble model Ensemble model is self-adaptive to satellite operating conditions because it has a lot of based model. I mean, different based model can deal with different operating conditions. Because this ensemble model is training gradually, so it can self-adaptive to different operating conditions switching. And the training process is to optimize or minimize the objective function. And the first part is the training loss, and the second part is model complexity. So, like for example, cherry boost is some kind of gradient boosting regression, and it is very good. It is a very good regression. We can eliminate the feature from X1 related variables that has the lowest score. We do a lot of training. After each training, we get the feature importance or feature scores. We eliminate the least important feature scores. And we do it again and again. We can filter out the more important features, so we can get the recommend association in this way. And see a problem. We can see an example. So we take satellite power subsystem as the research object. However, the application scope of the method is not limited to the power subsystem. For satellite, the power subsystem is responsible for power supply to whole satellite, and it has great significance. And the concept, this picture stands for satellite power subsystem. It has this subsystem is mainly composed of solar array and battery pack, and some control unit like MEA module or BA module. It has the loads. It requires some current from the main bus, and the solar array can receive the sunshine and generate solar current. And the MEA and the BA can control the charging current and the discharge current based on the battery voltage and the main bus current and the sun. So this system can work under different conditions. And it has some different working conditions. So we picture the telemetry data from the system. We can see from the picture there are a lot of conditions. For example, this one, this one, this one. Under different for different working conditions, there are a lot of different patterns. I mean, for example, this pattern, this pattern is different. We can see there are a lot of patterns, different patterns. So we want to find the patterns. We want to find the association between these kind of different telemetry variables. In 9th and 10th round, which the error is much bigger than the error in the 8th round. And considering regression errors and the number of features, and it is easy to know that the correlated telemetry variables to MEA voltage, solar current, bus current, and BA voltage. So the 8th round is what we want. So we man the association by a recursively training. This picture is a display of MEA and its related telemetry variables. And we can use the gradient boosting regression method to train the baseline model, and MEA as the dependent variable, and the other stands for the independent variables. We do the regression training. So this is the training result. So it is shown that the regression value MEA regression, it stands for the regression result, and the MEA2 the blue one. The yellow one is stands for the regression, and the blue one is stands for the true variable. So from this picture, we can see that the yellow line, the blue line are close enough. It means the health baseline model, the prediction result of the health baseline model is very accurate, and it can self-adaptive to different working conditions. So from this picture, we can see a lot of different working conditions. And this one is this part, and this part, and this part. This part is for the shadow. When the satellite has no when the satellite in the shadow area, means this kind of condition. And this two is for some based on different different position and the and the sun, and so because we use the gradient boosting algorithm, and has a lot of based model, so different based model can deal with different working conditions. So from this picture, we can see that the health baseline model is really accurate. So the second step of the anomaly detection is we take the regression variable and the true variable, and we compute the error of these two, and we use the regression error to do the anomaly detection. So this picture, this is the regression error, and we use we set some thresholds. When the regression error is outside the threshold, and it stands for anomaly. It means, but we also these thresholds can be set by some operators, by manually set, and it also can be set by some statistical way from the training data set, from the training progress. We can do some statistical method to find the threshold. And if we don't want so much anomaly point, we can adjust the thresholds. And as a test case, we use the truly anomaly data set for the verification, for the validation. And so this is it shows that the anomaly detection method proposed in the paper can detect anomalies effectively. So this paper proposed a new anomaly detection method, gradient boosting regression algorithm, is to automatically learn the nonlinear complex functional association and then we train the health baseline model, and we get the prediction error, and we compare the two variables and the prediction one. We do the we get the regression error and use this error for the anomaly detection. So we use the power subsystem to verify the validity and the effectiveness of the method is verified by the telemetry data of the power subsystem. So thanks.
Dear attendees, I'm Liu Yuyan, the speaker of a new approach on satellite mission planning with revisiting requirements. With the development of the space science and technology, the demand of observation mission increases. However, due to the limitations of the performance of platform or payloads and the space environment of the remote sensing satellite, the observation ability is restricted, so it's necessary to carry out the mission planning, aiming at the observation task of revisiting hotspots by remote sensing satellites. This paper firstly analyzed the practical constraints and designed several functions about optimization goals. Secondly, the mathematical model was established. Thirdly, the algorithm to solve the problem was based on PBRL. Finally, to examine the performance of the algorithm, this paper creates simulation scenarios and test cases by means of STK, and obtains the initial simulation time window sequence. By comparing with the results of GA, the effectiveness of PBRL algorithm in solving the problem of multi-satellite revisiting mission planning has been verified, which is better than the results of GA. And then, the first part is introduction of research status at home and abroad. Scholars from all over the world have studied satellite mission planning from multiple perspectives, including overall problem and analysis, algorithm implementation, software implementation, and analysis of different constraints, and so on. In terms of comprehensive materials, most of studies focus on overall or large area coverage, and the revisiting demand of hotspots is not fully considered, and as you can see, they also use a lot of smart algorithms, but using PBRL algorithm is rarely used to solve such problems. Therefore, based on previous studies and taking small satellites as research objects, this paper designed a population incremental learning algorithm to solve the problem of revisiting mission requirements, and compared the results with genetic algorithm, conducted simulation experiments on multi-star time window sequence to verify the effectiveness of the algorithm. And then the second part is description of the problem. The first is a brief problem overview. During the observation mission, the satellite carries a sensor as a payload to observe the Earth and collect information, and then sends them down to the ground station. In the case of multi-satellite operation, the observation task is determined, the resource utilization rate is improved, and the observation effect is optimized. In this paper, the basic input elements of regression usually including satellite orbit parameters, payload parameters, satellite platform parameters, and the geographic location of targets. There are two basic output elements of the problem. one of which is the mission planning scheme, which can be represented by a structure including the satellite number of the corresponding mission, the number of the ground target, the starting and ending time of the observation time window, and whether the window is selected or not, and the other is the expression of the observation effect. The constraints of the problem is related to the authenticity and accuracy of results, so it needs to be combined with the actual situation to determine. In this paper, we consider power constraints, storage constraints, sufficient attitude adjustment time for observation, and time window conflict, which means a satellite can only observe one target at a time, and in order to improve resource utilization, the same target can only be observed by one satellite at the same time. This study is a phased planning for multiple points and small areas. Therefore, the optimization goal has been adjusted accordingly. The most important optimization objectives are total number of observation and total observation time. The second objectives are average visiting time and mean variance of visiting time, which can be used to judge the uniformity of the time windows. And then the following part is the introduction to design of population-based incremental learning algorithm. Incremental learning refers to a system that constantly learns new content from the outside world and updates the content learned. And population-based incremental learning is based on our population and regards the evolution of a population as a learning and updating process, and uses the required knowledge to guide the generation of the next generation of population, thereby producing a better solution of fitness values results. It is possible to model the optimization process of population in genetic algorithm for processing and analysis. The chromosome coding and initial generation, as well as the determination of fitness evaluating function, are described in detail in this paper. It's worth mentioning that various conflicts are excluded before fitness calculated, and this is a follow chart of PBRL. The first step is to load data and code it. In other words, the sequence obtained in the previews are first sorted by initial time of time window, then sorted by the satellite number, and then according to whether the satellite time window is selected. 1 means selected, 0 means not, to number them, and then generate initial population, calculate fitness before excluding conflicts. If stop condition is met, output the sequence of match windows. If not, compute the learning probability matrix and produce the next generation population. I would like to introduce the difference between two algorithms. PBRL algorithm is to improve the learning probability matrix by learning the good chromosomes in the previous generation and the reasonable probability of variation, just like these volumes. Thus, it can be seen that learning rate alpha has great impact on the algorithm, which requires careful selection. It is well known that GA is a computational model of the biological evolution that simulates the natural selection and the genetic mechanisms of Darwin biological evolution. Therefore, the GA generates the next generation through the selecting operator, the crossover operator, which is random selection of two individuals for single-point crossover to obtain offspring, and the mutation operator. The specific process is also explained in the paper. In order to improve efficiency of genetic algorithm, we also adopt elite retention strategy. And the fourth part is the examples and analysis. This page shows the satellite and the target data used in the example. By analyzing and discussing influence of orbit parameters on the regional coverage, we finally determined the constellation. In order to highlight the comparison results, some factors adopted by two algorithms are constant, such as the probability of variation. It is feasible to apply PBRL to satellite mission planning problem, and it can achieve convergence within a certain irritation range with a good convergence result. Results that can take into account secondary optimization goals are added to this table, just like P123 and P223. And then this page is the set at the time window plan for example 1, and this is a partial magnification of it. Different colors represent different ground targets. And the genetic algorithm also gets similar results. It is obvious from above two figures that GA is applicable to solve this problem, and it can also achieve convergence within a certain irritation range with a good convergence result. And in the last part, we can compare results from convergent value, irritation times of the window fitness, and the CPU computing time. As long as the number of the convolutions is sufficient, they will converge equally. It can be clearly seen from the pictures above that PBRL algorithm rises faster than the GA in the initial stage, because the population generation of PBRL algorithm is based on a specific learning probability with strong orientation, which can make the individuals in the whole population irritate in a clear optimization direction, while the GA needs to drive the population to change optimally through two ways: elite retention strategy and choosing two excellent ones from parents and two children. So the orientation is relatively weak. It is worth mentioning that the calculation time of GA is almost twice as much as that of PBRL algorithm. The calculation examples shows that it's reasonable and effective to use this method to solve similar problems. It also shows that the performance of the population incremental learning algorithm is superior to the GA. It should be pointed out that this paper only achieved the research result in a certain aspect, and the research on observation constraints is not sufficient. Other more complex constraints will be first considered in the future, and the algorithm will be first optimized for the actual application. In the end, thank you for your listening.
My name is Lei Mingjia. I'm a PhD student in Harbin Institute of Technology. It's my pleasure to have this opportunity to report our research. Today, I'd like to say something about the fault diagnosis of satellites. This presentation consists of 5 different parts. Let's get to the point. The first part is a brief introduction of the purpose and the background of our research. The Satellite Attitude Control System is an important subsystem to guarantee the on-orbit operation and mission execution of the satellite. Therefore, it is of great significance to improve the health monitoring ability and fault diagnosis accuracy to ensure the reliability of satellite. Generally, the Satellite Attitude Control System has a variety of telemetry signals and a large amount of data, which provides a databasis for the attitude control system fault diagnosis and health assessment. There are more and more studies on satellite fault diagnosis from the perspective of data. The current research can be divided into 2 categories. Research is based on single source data and research is based on multi-source data. With the deepening of research, the advantages of multi-source data in information expression completeness and accuracy are prominent. So in recent years, the research on satellite fault diagnosis and health assessment gradually tends to focus on multi-source data. So how should we use the multi-source telemetry data? With more and more variants of telemetry data used for fault diagnosis, the traditional methods based on threshold and expert systems are limited in practical application due to its poor time effectiveness and impacts caused by human factors. In order to make up for the shortcomings of traditional methods, many machine learning and deep learning algorithms have been applied. Although there are lots of researches on fault diagnosis methods, the importance of parameters which used for diagnosis is seldom studied. However, as the satellite system itself is a complex system with high coupling, there are intricate relationships between satellite telemetry data. And these relationships often have a great impact on diagnosis results. Hence, the importance of telemetry parameters in the process of fault diagnosis can be analyzed to assist computers or experts to make further a judgment on satellite health status. In our research, a parameter importance in a measurement method based on DBN is proposed to measure the abundant telemetry signals. This method enhanced a constraint of the number of underlying nodes and the constraint of connection weights of DBN. It trains the network based on the contrast divergence algorithm and then obtains the parameter importance weight matrix based on RBM. The test on the satellite momentum wheel telemetry data set proves that this method can effectively improve the accuracy of fault diagnosis. In the second part, the method of parameter importance measurement based on deep belief network will be claimed. The deep belief network proposed by Hinton is a generative model which consists of several restricted Boltzmann machines. The RBM is a generative stochastic neural network that contains a visible layer and a hidden layer. The variables of both visible layer and hidden layer are binary. That is, their states are taken as 0 or 1. As the figure shows, there is no mutual connection between neurons on the same layer. The connection between connectable neurons is bidirectional and symmetric. Usually, the visible layer is used as the input layer of the data, and the hidden layer is the output layer of the generated data. RBM is an energy-based model, denoting its visible layer as V and hidden layer as H. The energy expression of V and H are shown in equation 1 and equation 2. The learning process of an RBM is to find the optimal value of theta in order to fit the given input data. According to the joint allocation energy of V and H, the joint allocation probability can be obtained as shown in the equation 3. If the training dataset is assumed to contain n samples, the objective function can be expressed as the equation 4. The learning objective of RBM is to find the parameter set that can maximize the logarithmic likelihood function on the training dataset, and these parameter sets mainly include the weight matrix W connecting the visible layer and the hidden layer, and the bias vectors of the two layers. According to the above equations and the Gibbs sampling process, the objective function can be further derived as the equation 5. In order to sample effectively and efficiently, Hinton and his staff put forward a new algorithm that is the contrastive divergence algorithm. The idea of this algorithm is shown in the left figure. At the beginning of the algorithm, set the visible state of each node to a training sample and use the equation 6 to calculate values of all the hidden layer nodes. When calculating all nodes of the hidden layer, according to the equation 7, the probability of each node of the visible layer being 1 is calculated. So as to obtain the first reconstruction of the visible layer, then the reconstructed visible layer is taken as the real model and put into the formula of RBM parameter update to calculate the updated RBM parameter. The steps of training RBM with CDK algorithm is shown in the left figure. After introducing the RBM, we will focus on the DBN. DBN is constructed by multiple layers in the neurons, which are divided into visible neurons and hidden neurons. Hidden neurons are used to extract features of the input data. As shown in the left figure, the top two layers of DBN structure are associative memory formed by undirected graph model. The other lower layers are connected by a directed connection between the upper and the lower layers, forming a directed graph model. DBN is essentially a stack of RBMs, and the training process of DBN is carried out layer by layer. In RBM, composed of two adjacent layers, and the lower layer is the visible layer of RBM, and the data vector of the visible layer is used to infer the data of the hidden layer, and then the inferred hidden layer is used as the data vector of the next visible layer of RBM. To measure the importance of the telemetry data, we propose a method based on the DBN by constraining the number of nodes and the connecting weight matrix between the input layer and the first hidden layer of the DBN. The equation 8 and the right figure represent the constraints. These constraints mean that the number of nodes of input data is equal to the nodes of the first hidden layer. The Wij is the connection weight between the input layer node Vi and the hidden layer node Hj, and if I is not equal to j, the Wij is equal to 0. The importance coefficient of input data can be obtained through network training. The parameter importance measurement method based on DBN is shown in the left figure. In the third part, we studied the specific method for the fault diagnosis of the altitude control system based on PIM-DBN. There are many types of telemetry data for the satellite altitude control system. In our research, 10 kinds of parameters are selected as the fault diagnosis parameter set, which contains rotate speed, voltage, current, temperature, friction moment, acceleration, and so on. The structure of PIM-DBN is shown in the Table 1. There are 5 hidden layers in this structure, and the first hidden layer has the same 10 nodes with the input layer. The training algorithm of PIM-DBN is designed based on DBN training algorithm, and it has 2 sections. The section 1 is unsupervised pre-training, and the section 2 is supervised fine-tuning of parameters. The specific process is shown in the slides. In the fourth part, we will take momentum wheel telemetry parameters of the satellite as an example to verify the effectiveness of the proposed method. The original telemetry parameters used in our research are shown in these figures. In order to study the importance of the telemetry parameters of the momentum wheel in the fault diagnosis problem, the data are divided into time periods, and the time periods include 6 modes. They are normal acceleration mode, normal acceleration mode, normal deceleration mode, normal stable mode, abnormal acceleration mode, abnormal deceleration mode, and the power down mode. The training set and the testing set are shown in Table 2. The number of training samples is 3,000 and the number of the testing samples is 1,000. We applied the PIM-DBN method to quantify the importance of the above 10 parameters. The results are averaged by 10 trials to reduce the randomness. The importance weights of satellite momentum wheel telemetry parameters based on PIM-DBN are shown in Table 3. It can be seen from Table 3, rotate speed, voltage to current, friction moment, and acceleration have higher weights, while the weights of the temperature-related parameters are lower. This result is consistent with the actual situation with the momentum wheel. Since the temperature-related parameters are greatly affected by lighting factors and less affected by the working state of the momentum wheel, and the weights of the above four temperature telemetry data are related lower in the fault diagnosis. On the contrary, the working state of the wheel is closely related to its rotate speed, voltage, current, friction moment, and acceleration. So the weights of the above 6 telemetry data are relatively higher in this case. To compare with other methods, the support vector machine, artificial neural network, and the DBN are used for the original date and the importance weighted date respectively. The results are averaged by 20 trials to reduce the randomness. The diagnostic accuracy is shown in Table 4. According to the result in Table 4, the accuracy of fault diagnosis based on DBN is higher than the net based on SVM and ANN, and the fault diagnosis accuracy of the above 3 methods on the weighted date is all improved. The result shows that the parameter The parameter importance measurement method proposed in our study can effectively improve the accuracy of fault diagnosis for satellite altitude control system. The last part is conclusion. The main contributions of this study are proposing a new method PIM-DBN to calculate the importance of parameters and applying this method to the fault diagnosis field. The proposed method was tested on the telemetry dataset of satellite altitude control system. In this study, importance weights are learned for 10 types of telemetry data. The original data are weighted data, and the weighted data are used for fault diagnosis with different methods, such as support vector machine, artificial neural network, and deep belief network. All the methods obtained higher accuracy by using weighted data. These results show the good potential of the proposed method in the data-driven fault diagnosis field and the health assessment field. That's all. Thanks for your attention.
Dear teachers and friends, it is a great honor to present academic achievements of our team to you through the network as the author's representative. My name is Wang Ruixing, and the team include Professor Li Yuqing, Zhang Hailong, Liu Fan, and Lei Mingjia. Among the team members, Professor Li Yuqing, Lei Mingjia, and I am from School of Astronautics, Harbin Institute of Technology, and Zhang Hailong and Liu Fan are from the Xi'an Satellite Control Center in China. In the following description, I will display our academic achievements from 4 aspects. The subject background. In this part, I will elaborate on the problems solved by the research of the subject as well as its engineer value and significance. Then subject programs. That is, in what way to solve the problem first. Then subject results. In this part, I will demonstrate the simulation demonstration system designed in the process of the research and present the research results of my team in a very intuitive way. The last subject summit. In this part, I will some background significance, research approach, research results of this research process in a more clear way, and the problem still exist deficiencies and further research plans in order to solve the report and the study clearly. Part 1. Subject background. We know any work in the space field have extremely demanding requirements on reliability and accuracy, no matter it is the design and maintenance of significance, or the evaluation and decision of spacecraft, because the space industry investment is huge, and the space volume is huge, and the system is complex. The research of Earth is the decision problem of spacecraft. The spacecraft health evaluation and the space fault diagnosis has been studied extensively in the past. Although the problem is very complex, more effective and perfect research method has been formed after years of research accumulation. Among them, there are health evaluation-based fuzzy variability with principle and analytics, heuristic process, and so on. It can be said that the satellite health evaluation system is clear because the difficulty in the construction of the evaluation system of health evaluation is not very great. The main obstacle to solve such problem is to choose or design a more effective evaluation method. Comparison. Support for satellite mission effectiveness research involved now in this earth is less, because that is not to say that this problem does not have great research value. On the contrary, it has very profound research significance, just because when you solve the problem, you need to deal with two more complex sub-problems at the same time. One is construction evaluation system. The other is evaluation methods selection and application. However, the construction of evaluation system is particularly complex. That's all. We can see there are two research fields. One is satellite health evaluation. The other is satellite mission support efficiency evaluation. We can see for satellite health evaluation, there is one problem to be solved. That is the selection of evaluation method. But for satellite mission support evaluation, there are two problems. One is the selection of evaluation methods. The other is the construction of evaluation system. So, the satellite mission support efficiency evaluation is more difficult than the satellite health evaluation. For a more practical case, if you are a decider of satellite system task with a current signal of remote task, you know the load of the task and the satellite relative performance parameters and the other quantifiable data that will make the task of decision making. Decision making may be under the current signal whether should perform the task, which satellite are invoking to perform this task, and so on. We know how difficult decision making is. If you are a very authoritative satellite experts in this field with decades of work experience accumulation, the abundant satellite system work is, perhaps it can become easier. You can recall past work, learning, knowledge, and experience accumulated in the process of satellite, which can help you make the decision. However, on the one hand, this process is affected by the strong subjective factor of the individual, and this problem requires a great deal of accuracy and timeliness. So it also requires a high quality of decision maker. Fortunately, with the full development of artificial intelligence and other optimization efforts, we can adopt more intelligent ways to solve such problems. However, if we want to replace the expert scoring method by an intelligent way, we will have to deal with two more complex sub-problems. That's how to build a complete evaluation system and how to choose an effective evaluation method. To sum up, this kind of problem has high complexity, but also has extremely important engineering value and research significance. The second part, subject program. In response to the above two problems, on the basis of a large number of references, our team created a Cascade decomposition method, which decomposed satellite mission at metropole level, such as task level, attribute level, method level, and input level. The method is based on base information such as satellite health status and environmental risk. Therefore, the construction of the complex satellite effectiveness evaluation problem become rule-based and provide theoretical guarantee for the completeness and the system during the construction process. On the basis of construction a good evaluation system, it chooses a very effective evaluation method that is well matched with the system construction method. That is the base network method, which has a very good performance in the field of causal reasoning and decision support. Among them, the diagram of Cascade decomposition is shown as follows. The mission is decomposed step by step so as to connect the decision output with the template input, and finally represents the invisible black box between the two. After the completion of this process, we will get a very effective system construction process. And after application this theory to the practical problems, we will get a very complete evaluation system. Taking remote station mission, for example. On this base, the adequacy and effectiveness of Bayes network method in this problem are fully guaranteed. Here are the satellite thermal control system health evaluation or Bayes network diagram. Left and right side of the picture are the two important parts of the Bayes network. On the left of the network, on the left side of the network, parameters in the Bayes network. The network structure of the Bayes network is on the right. In this series satellite mission effectiveness evaluation problem, the Bayes network structure is determined by the above-mentioned method of Castle decomposition method, and the left side in the form of conditional probability tables. Bayes network parameters is through the network learning authority to determine. The training data required in this part can be scored by experts and determined based on previous engineering experience. Through the wing of learning-based network, parameters determine the causal relationship between the different levels. Finally, on the basis of input data, reasoning the results, then obtain degree of satellite support for the mission in the form of percentage. Ultimately, support decision making. We can see the evaluation system determined by the causal decompose method is taken as the network structure of Bayes network, and then the network parameters of Bayes network are determined by parameter learning. This is the following chart for the all satellite mission support performance evaluation. Part 3, Subject Results. As for the research achievements in this subject, our team makes the simulation system YC++ languages. The simulation system is to evaluate the effectiveness of the Earth remote station mission. The figure shows the mission flow of the satellite remote station, which is helpful to reasoning construction of the evaluation system. The pool of simulation system for satellite remote station, including satellite components health degree, in order to calculate process smooth. The health degree of satellite system components were probably normalized with a finding between 0 to 1 instead. In addition, there is also the performance of subsystem, which can refer to the design of the satellite, as well as the safety degree of the space environment and the external influence of the satellite environment. As for the output, the simulation system provides output of multiple dimensions, among which the most critical and the most important is the support performance of the mission. This output directly reflects the support efficiency of the satellite evaluated for the mission under the current situation, which is also the most direct result of technical support for the mission decision making. In addition, results is shown in the figure in the form of percentage. The fourth part, subject submit. Based on all the above contents, it can be said that this research has great research value and significance. First, it innovative the evaluation framework theory on complex performance evaluation problems, and then selection the Bayes network method, which is very consistent with the Cascade decomposition method as evaluation method. Such smoothly completed the problem or research. Finally, through the application of the simulation system, it can be said that this method has strong vividity and completeness. As for the following work, we will further improve the Cascade decompose method so as to expand the brains of each application. The above is the whole content of my report. Thank you for your listening.
Hello everyone, the paper I report is Data Management of Space Station Bus Network. First, introduction. China's managed space projects are implemented in accordance with three-step development strategy. The first step is to start with a managed spaceship. The second step is to launch a space lab and realize rendezvous and docking. The third step is to build a large space station. Bus network data management belongs to the onboard data handler system, which is the key component of space station. It's responsible for the bus communication management in each capsule and the bus management function between capsules of the space station. In the process of rendezvous and docking between each capsule and a capsule of the space station and the transport spaceships, the bus network data management is responsible for establishing the docking bus network among multiple spacecrafts, realizing the functions of telecommand, command transmitting, telemetry data collection, and control data transmitting. Second, missing characteristics. China's space station consists of kernel capsule, experimental capsule 1, and experimental capsule 2. There are independent and combined flight modes between multiple capsules of the space station, and the mode of rendezvous and docking with multiple managed spaceships and cargo spaceships is complex. These tasks put forward the following requirements for the design of bus network data management of the space station. Firstly, ensure the reliable transmission of information under the independent and combined flight modes of three capsules. Secondly, requirements for integrated networking and data communication between the spacecrafts and within one spacecraft. It's necessary to design a unified communication protocol and data format to realize the integrated networking, and communication among the spacecrafts. Thirdly, hierarchical management of multiple bus networks. The category of 153B bus network includes the main bus network, combination bus between the three capsules, docking bus with transport spaceships, and secondary bus networks within the subsystems. Third, design of bus network. The bus network is designed in a hierarchical way. The first level bus is used for the main control of the whole capsule, including the system bus in the capsule and the docking bus between the spacecrafts. The system bus in the capsule manages the main computer equipment of each subsystem. The docking bus manages the communications between the capsules and the spaceships in combination mode. The second level bus is used to control and manage the equipment in each subsystem. The kernel capsule is connected with experimental capsule 1 and experimental capsule 2 through the docking bus to form a combination, which forms the whole space station. Each subsystem controller is connected to the first level bus as the remote terminal of the first level bus and the PC of the second level bus. The docking bus network is divided into two levels. The first level is the docking bus in the capsule, which is used to establish the bus communication link after the kernel capsule forms a combination with the experimental capsule 1 and the experimental capsule 2. The second level is the special docking bus with the transport spaceship, which forms a combination with the manned spaceship and the cargo spaceship respectively, and then establishes the bus communication link. In the special docking bus, the converter is designed to connect the space station network and the transport spaceship network. The converter plays the role of gateway and realizes the data communication and the protocol conversing between multiple spacecrafts. 4. Design of data management. Telemetry management realizes the process of telemetry acquisition, telemetry package, telemetry framing, and telemetry frame downlink. There are 3 levels in total. The first level is that each terminal device obtains telemetry data through sensors. The second level is that each subsystem controller connects telemetry data of the first level through the secondary bus and packages them. The third level is that the onboard computer collects telemetry packages of each subsystem controller, which are multiplexed to virtual channel frames to transmit and downlink. The Telecommand management function uses CCSDS Telecommand data link protocol to realize the Telecommand data receiving and forwarding function. The data format uses the standard data formats of Telecommand transmission frame, and the standard EPDU package is used in the data field. After receiving the Telecommand frame from the ground, the onboard computer processes the frame routing and the package routing respectively. The standard EPDU package is used for data transmitting among subsystems. APID is used to identify the spacecraft, the subsystem, and the data type. The onboard computer routes the package according to the package routing table and sends the EPDU packet to the destination device to support the data communication between the capsule and the spaceship. The main elements of the package routing table are designed as follows. Fifth, conclusion. Space station-based network data management is an important part of the space station mission, which involves the information management between the three capsules of the space station, manned spaceships, and cargo spaceships. The bus network data management special design in this paper can support single capsule independent flight mode, three capsules docking flight mode, docking and separation flight mode with manned spaceships and cargo spaceships, which is safe and reliable. Through the uniformed protocol design and routine management, the function of integrated networking and data communications between spacecrafts and within spacecrafts is realized. The method has been tested and verified in the space station mission. That's all. Thank you.
Hi everyone. I'm honored and proud to have the opportunity to speak at this conference. I'm Qiao Liang, a software engineer at China Academy of Space Technology. Today, I would like to present my paper, a space network-oriented spacecraft software high reliability maintenance method. In the first part of the report, I'm going to begin with the current status of spacecraft software maintenance method, and then I will indicate the basic process of software high reliability maintenance for space network angel reconfiguration. And next, I will discuss in more details about the key technologies of spacecraft software in orbit maintenance. And in addition, we have done some tests of the method. So in the fourth part, I will show you the test results. The first part, introduction. Currently, there are more than 200 in-orbit satellites in China, and most of which are designed for functional solidification. Also, these satellites are difficult to connect to the internet, resulting in the delay of information transmission, and the difficulty of cooperation among satellites, and the result in the high complexity of ground operation and maintenance, and the low efficiency of satellite application. However, current satellite users have increasing demands for agile reconfiguration and on-demand customization of the space network. The existing space network does not have the overall design for software architecture based on the software definition, and it's difficult to make the dynamic deployment and in-orbit reconfiguration for several types of inter-satellite links and multiple network nodes. The PROM chips that are stable, but these chips can be programmed only once. So the only way to reconfigure software is to remove the chip and reprogram the new software. Using programming once PROM chips have better resistance to spatial radiation, but makes software debugging difficult. Even worse, it's impossible to change the space network protocols after the launches of the satellites. And this programming method is not conducive to agile reconfiguration and on-demand customization of the topology and the protocols of space network. Another way to reconfigure spacecraft software is to change the data in RAM directly. But RAM is a kind of volatile memory. In the space environment, high energy particles often cause the computer to restart, resulting in the loss of software updates, which means disconnection from the network and the loss of communications. Therefore, in practical usage, this method also has many problems. In this paper, we propose a method using non-volatile memory, such as flash and EEPROM. In this paper, we propose a method of maintaining in-orbit spacecraft software orienting the agile reconfiguration of space network with high reliability. First of all, this paper introduces the basic process of software in orbit maintenance based on non-volatile memory. Then, this paper introduces several key technologies to ensure the reliability of software in orbit maintenance. Finally, we introduces the effectiveness of this method by introducing the test results. The second part is the basic process of software high reliability maintenance. Compared to common embedded software, there are three main differences in the in-orbit maintenance process of spacecraft software. Firstly, the ground station cannot connect the satellites at all times. So, it takes a long time to send and execute the reconfiguration telecommands of the entire space network protocol. Secondly, the telecommand channel is a wireless channel, which has a relatively high error rate. Thirdly, high energy particles in the universe can be projected into the sensitive area of the semiconductor devices, resulting in single event effect. Therefore, it's necessary to detect and repair errors continuously while the program running. taking into account the needs for maintenance of spacecraft software with space network function. As shown in the figure, we designed the maintenance process of in-orbit software suitable for agile reconfiguration of space network. After starting the spacecraft onboard computer, the program data in the EEP room is moved to RAM and run in RAM. If the program has to be modified in orbit due to the updates of software parameters or the space network protocols, the data in RAM can be modified directly. If a permanent update is needed, it can be written with the whole or part of the new version of the in-orbit software in EEP room. In order to resolve the high dynamic performance of space network and the relatively high bit error of the uplink channel, and to achieve the high reliability of the software maintenance process, the uplink telecommand instructions from the ground are temporarily stored in RAM. After receiving all instructions, the running software compares the check code attached to the instructions with the check code calculated from the data temporarily stored in RAM. If the verification is correct, the reconfiguration data is written to EEP room. So in this way, the reliability of the communication is improved. And in addition, another common method is TMR, that is triple modular redundancy. That is to store the same data in 3 pieces of memory. The third part is the key technologies of spacecraft software in orbit maintenance. The first key technology is high reliability EEP room data maintenance. So a single high energy particle in the universe can be projected into the sensitive area. So it may cause single event effect. And the redundant design for EEP room is very important for the reliability of the space network. But however, it should be noted that when writing EEP room, the tunnel oxide layer would withstand high voltage and high electric field, so the lifetime of the EEP room is limited. To extend the lifetime of EEP room and to prevent in-orbit failure of EEP room, the frequency of self-detection of EEP room should not be too high. The second key technology is the reliability design of in-orbit reconfiguration telecommand instructions. The first one is verification of the instruction format. So software checks the instruction fields according to predetermined format, including the instruction verification code format comparison, and optional range of each field, and the validity of memory addresses to reconfigure. So the second The second one is comparison of the Telecommand instruction code. And the third one is continuity check of the serial number of instruction packets. So to write a large amount of data to EEPROM, it's necessary to divide the large instructions into several packets. And the onboard software will receive these packets in sequence. In case of the packet loss or packet serial number error, it will alarm the ground station by telemetry channel to ensure the integrity of the instructions. The fourth one is the temporary storage in RAM. In order to further improve the reliability of the reconfiguration instructions, we also designed a method to store temporarily the reconfiguration data in RAM. After all the data have been received, the verification codes should be compared with the calculated code. If the two parts are matched, the reconfiguration data will be written to EEPROM from RAM. The fourth part is engineering design and test verification. So this figure is a typical computer architecture. So the CPU board of a high orbit satellite platform computer as the core, and constitutes a complete computer system with other modules including memory and bus controller, high stable clock interface, and so forth. And also we also constructed the test environment. The test environment is composed of the main control computer, test client, line network, cables, and test software. And the main control computer controls each test client, and all test data and test results can be displayed and processed on the main control computer. And also we designed a lot of tests to verify the method. So the tests including single bit error test and double bit error test. And also we did some tests to verify the software reconfiguration process. And first, we compiled the whole program, continued the new SpaceNet network protocols into executive files. And then the packets were injected into the spacecraft computer system through the ground test software in sequence. And we checked the check code and checked the order and the quantity of received instruction packets. After the restart of the computer, the newly program was started by EEPROM normally, and the new space network protocols ran correctly, which proves the correctness of the software reconfiguration process. In this paper, a space network-oriented spacecraft software high reliability maintenance method is proposed. Firstly, the limitation and shortage of the using one-time programmable PROM to program the spacecraft software are analyzed. Then, based on the characteristics of APROM, the basic process of high reliability maintenance for onboard software is introduced. And then several key technologies of in-orbit software reconfiguration and data maintenance are introduced in details. In the end, this paper describes the engineering design and analyzes the experimental verification of the in-orbit software maintenance method. The test results show that the method can realize in-orbit reconfiguration and data maintenance of space software, meet the design requirements, and improved the in-orbit maintainability and accessibility of space network. That's all. Thank you.
Hello everyone. My paper's topic is the design of an LEO Constellation satellite integrated electronics system and the reliability analysis. The paper divided into 5 parts. Number 1, introduction. Number 2, analysis on OneWeb Constellation satellite integrated electronic products. Number 3, the design and realization of a domestic LEO Constellation satellite integrated electronics system. Number 4, reliability prediction analysis on the LEO Constellation satellite integrated electronic system. Number 5, conclusion. Number 1, introduction. To solve the problem of the internet access in rural areas and other remote areas, satellite internet has become an inevitable trend for the combination of satellite communication and the internet. The OneWeb satellite system, a LEO Internet satellite constellation system, rapidly developing in recent years, is indicated to providing terrestrial users with high-speed broadband space-based access services. There is still a certain gap between the domestic system and the required. It is imperative to develop a satellite-based high performance, high integration, and low-cost integrated electronic system for LEO Internet Constellation satellite applications. The study on the OneWeb and other foreign advanced LEO mobile constellation related technologies might provide good references for the development of domestic system. An integrated electronics system for LEO Internet Constellation satellite applications was designed in a paper upon the foundation of benchmarking foreign advanced products. Number 2, the core of the electronic system for the OneWeb Constellation satellite platform is the amethyst integrated electronic system designed by Airbus. Functions including on-orbit redundant computing and processing capabilities. TMTC that satisfies CCSDS GPS reception, secondary power distribution, attitude and orbit control sensors, and actuator interface, time and space partitioning of space software, etc. MSET integrated electronic is composed of 4 modules in 2 categories, namely the core processing modules and the interface expansion modules. When designing the integrated electronic system for domestic LEO Constellation satellite platform, we can also draw on this idea and benchmark its technical parameters to meet the service needs. Number 3. 1. Overall architecture design. Constellation satellite integrated electronics integrates traditional platform telemetry and telecontrol units, a satellite housekeeping computer, business units, a control computer, a GNSS receiver, a star sensor circuit box, an array driver circuit box, and other functions into a central management unit. The system uses CMU as a main control terminal, and the components are connected through databases to build a distributed network system. Based on the module division of MSET integrated electronic requirement, the above functional modules can also be divided into 2 categories: the core processing modules and the interface expansion modules. An interface expansion module includes command acquisition, load communication, sensor communication, attitude and orbit control drive, power distribution, GNSS, and other functional modules. A core processing module includes 2 major functions: data management and telecontrol, which specially cover CPU core system, time management, system bushes, inter-satellite, Earth measurement and control communications, measurement and control, encryption and decryption, important data storage, and large volume data processing. The core processing modules are divided into the active and standby machines, configured in 2 panels with complete same functions. Among them, the satellite, Earth telecontrol, and important data storage proceed with dual machine hot backup, where the rest proceed with dual machines cold backup. CPU selection. The core issue for core processing modules is the selection of CPU. MSET uses a dual-core ARM processor with a performance of 215 MIPS. Considering from the perspective of independence and controllability, domestic Constellation satellite integrated electronics should use the domestic GPU, the new generation Spark V8 structured BM3823 processor was selected as a CPU. Bus selection, we refer to sister integrated electronics for the internal bus of the domestic Constellation satellite integrated electronics. The internal buses were divided into high and medium speed and low speed ones. Spaceware bus was selected for the former, where CAN bus was selected for the latter, realizing a general, modular, and standard design. 2. Overall structure design. The structure plane of CMMU should also meet the requirements of the module design, standardization, and scalability. In view of the large power consumption of the single board, the cage drawer structure was proposed. The system weighted no more than 5 kilograms, and the overall power consumption was 20 to 50 watt. Then we finally obtained the domestic LEO Constellation satellite integrated electronic system that can benchmark sister integrated electronics and have a similar overall performance. Number 4. The sister onboard computer has the service life of 10 years, and the computer reliability at the end of the service is not less than 0.59. In order to benchmark the sister satellite-based computer, we set a same reliability requirement on the domestic LEO Constellation satellite integrated electronics. The integrated electronic solution was provisionally determined to contain 6 function modules, of which the active and standby processor modules accounted for 1 panel each, and the active and standby modules of the other 5 functions share a panel. For the analysis convenience, it is assumed that the failure rates of all models are the same, and the failure rates of the module does not change with time. The following several working modes were considered, including the dual machine standby backup mode for whole machines switch over, the multi-machines parallel backup mode, the backup mode for module switch over, and the repairable dual machine mode design. It was assumed that the failure probabilities of the system and the system components followed the exponential distribution. The failures of the system components were independent of each other, and the system components had only 2 states, normal or failure, and there was no intermediate state. 1. The dual machine's backup module for whole machine switchover. This is the block diagram of dual machine's backup reliability. We adopted the dual machine backup working mode. It was assumed that the two single machines' components were completely the same. The single machines is switched for switchover. The reliability of the switchover control part is 1, and the internal machine modules of the onboard computer form a several and then parallel structure. 2. The multi-machines parallel mode. Based on the one description, a change was made to increase the number of parallels. It was assumed that all functions of the single machines was all realized on one panel. A panel accounted for single machines, and a satellite-based computer is composed of several same single machines. A switchover is based on a single machine, and the reliability of the switchover control part is 1. Three, the dual machine mode for function mode switchover. This is the module of the reliability under the dual machines module switchover mode. The repairable dual machine mode. The onboard computer performs single machine switchover mode. The reliability of the switchover control part is 1, and the internal modules of the computer form is several and then parallel structure. Because the service cycle is relatively long, the steady state availability of the computer can be used to characterize the reliability at the end of the service. This is the estimated module failure rates. When the failure rate is constant, adopting advanced technology to reduce repair time can contribute to a relatively high repair rate of the onboard computer, make it much higher than the failure rate, improve the availability at the end of the service, and thus improve the onboard computer reliability. Number 5, conclusion. Upon backmarking foreign advanced LEO Internet satellite electronic system products, an integrated electronic system for LEO Internet Constellation satellite applications is designed in the paper. By using the new domestic high-performance processor and adopting a module design idea, the system is characterized by high performance and high integrated. Besides, targeting the service requirements on long service life and high reliability of the integrated electronics, and the reliability under different working modes was analyzed with the components stress analysis method and reliability improvement plan based on orbit repair was proposed. Finally, we obtained a design plan for satellite-borne integrated electronic system for LEO mobile constellation applications, with the overall performance comparable to those of the advanced foreign solutions. It meets the needs of domestic LEO mobile constellation service. That's all. Thanks.
A novel protocol and layered implementation for spacecraft telecommand and device management. In this paper, we introduce a new protocol based on Telecommand Space Data Link Protocol and a novel layered implementation of the protocol, which enables interpreting and forwarding uplink data, device management command, and manual control command through unified protocols, processes, and modules. Comparing to traditional protocol and implementation of spacecraft telecommand, the new protocol and corresponding implementation has great advantage in terms of standardization, flexibility, and extensibility, and has been applied to a large spacecraft assembly. With the emergence and development of various complex space missions, such as spacecraft rendezvous and docking, more collaborative controls and data interactions between different types of spacecrafts and between devices within spacecraft are needed. Besides, the standardization of inter-spacecraft and intra-spacecraft information exchanging interface is expected to be enhanced constantly. In this paper, we propose a unified protocol and corresponding layered implementation for spacecraft telecommand and device management, which is standardized inter-spacecraft and inter-device space interfaces. In the implementation, the Telecommand Space Data Link Protocol are strictly followed. The interfaces between layers are clearly defined, and each layer can be independently expanded to meet the requirements for various types of collaborative controlling, information interaction, and system rebuilding in the large orbiting spacecrafts. The data management system DMS is in large-scale spacecraft assembly needs to process and forward commands from different sources. Typically, there are two types of commands. Uplink telecommands from more than two physical channels which are from different telecommand systems. Manual commands and device-to-device commands from more than 3 members spacecraft in the spacecraft assembly. The process of forwarding command includes multiple steps: collecting command from bus, storing, verifying, and passing data, addressing and routing, packing and delivering message.
In traditional design, for each source S, there is a unique data processor DP to forward commands from S. Assume the average complexity of DP is C0. Let C1 denotes the complexity of DMS in single spacecraft, and let C0 denote the complexity of DMS in the whole spacecraft assembly. It's easy to know C0 increase quadratically with M, which is the number of member spacecraft. Obviously, the design is not scalable and extensible, and is not suitable for DMS in large-scale spacecraft assembly. The key problem in the traditional design is that the data structure used in different channels and sources are different, and thus make the DP not shareable. So we propose a new design of DMS which can unify the data structures and make DP shareable, so that the complexity of DMS in the whole spacecraft assembly will not increase with the number of member spacecrafts. At the same time, the extensibility and the scalability of DMS is improved significantly because the DMS in all existing member spacecrafts does not need to be upgraded when a new member spacecraft joins the spacecraft assembly. There are some key challenges in the new design. For example, there are one USB channel and several relay channels in a large-scale spacecraft assembly, and each channel has its own telecommand system. The length of telecommand frame, transmit rate, and other are significantly different. To ensure the DP for telecommand can be unified, the new design of data structure for telecommands must be adaptive to the characteristics of different physical channels. So in this paper, we propose a new data structure for uplink telecommand that can improve the utilization of channel bandwidth and simplify system design. The telecommand frame of different channels is filled with variable length transfer frames, which share the same format. The variable length transfer frames adapt to variable transmit rate of different channels. Device-to-device command is the command sent actively from any device in assembly to other devices. Manual command is the command sent actively from astronaut to devices. In traditional design of DMS, those commands are often implemented as customized simple command in private format, which can't be addressed in large scope and thus can't meet the needs of forwarding command multiple times among multiple spacecrafts. In this paper, we propose a new way of defining and implementing device management command that can support transferring any device-to-device command and manual command on the bus network in assembly. The structure of data frame is the same as telecommand transfer frame, except the length of frames are different, so that the telecommand and device management command can be processed and forwarded in a unified way. to improve the utilization of system resource and reduce the overhead of bus. The length of the frame for device management command is only the length of the command data packet plus the length of frame primary header. Referring to the standard of Telecommand Space Data Link Protocol, a transfer frame consists of frame primary header, frame data field, and frame error control field, as depicted in this figure. The frame data field contains one or more telecommand packets, which consists of packet primary header, packet secondary header, application data, and the packet error control field. Several identifiers are put in the data structure to support command processing and forwarding. In the frame primary header, there are spacecraft identifier, which is used for distinguish different spacecrafts, and the virtual channel identifier, which is used for distinguish different users in one spacecraft. In the packet primary header, there is application process identifier that is used for identifying a unique device. Based on the layered data structure defined above, DMS can forward user data from different sources and to different destinations transparently, and thus significantly enhance the flexibility and scalability. To unify the process of uplink telecommand and device management command (DMC), we use the same data structure to represent DMC, as depicted in this figure. The frame data field of DMC contains a command source packet and padding zeros, which are used for ensuring the size of transfer frame can reach the lower limit of size of transfer frame. The command source packet follows the same data structure as the telecommand packet. Based on the data structure for uplink telecommand and DMC, in this paper, we propose a layered DMS implementation mechanism to simplify and unify the process of executing and forwarding uplink telecommand, device management command, and manual command. This figure depicts the layers defined in DMS and how data flow passes layers. There are 4 layers in DMS: application layer, transport layer, network layer, and data link layer. Including data link protocol sublayer and sync and channel coding sublayer, the design of interface between layers has referenced the space communications protocols of CCSDS. Compared to traditional telecommand implementation mechanism, the new layered implementation mechanism proposed in this paper has advantages on almost all aspects. The table shows the result. Overall, the new mechanism has great advantages over the traditional telecommand implementation mechanism in terms of protocol standardization, system flexibility, scalability, and extensibility. The layered implementation mechanism proposed in the paper for telecommand and device management has been applied to the DMS of a large spacecraft assembly. The assembly consists of 3 independently orbiting spacecraft, which are interconnected by the docking buses. Each spacecraft is equipped with a data managing device as the bus controller, and all the three data managing devices have adopted the layered implementation mechanism. The bus topology and information flow are shown in this figure. We run the three data managing devices in laboratory and use simulator software to simulate RT on the bus networks of the three spacecrafts. To verify the new mechanism can work correctly, we keep the volume of data transmitted among the three data managing devices and the simulated RTS the same as the volumes of data in real orbiting system. The average volume of data transmitted on each bus is about 200 to 300 kbps. The dotted line 1 in this figure shows the example data flow of transmitting the DMS from device N to device 1 within the spacecraft 1. According to the data collected in laboratory, the latence of transmitting DMC between two devices in the same spacecraft is about 20 to 80 milliseconds. The dotted line 2 in figure shows the example data flow of transmitting telecommands from spacecraft 1 to device 1 in spacecraft 3. According to the data collected in laboratory, the latency of transmitting telecommand between two spacecrafts is about 120 to 550 milliseconds. The result of application validation shows that the DMS has adopted the layered implementation mechanism can forward DMC and telecommand among multiple devices and multiple spacecrafts steadily and reliably, and the latency of command transmission is low. It proves that the layered implementation mechanism can satisfy the needs of command transmission in large-scale spacecraft assembly. The layered implementation mechanism for telecommand and device management proposed in this paper has been successfully applied to a large spacecraft assembly. With the new mechanism, the commands for each spacecraft in the assembly can be injected through a unified physical channel and be transferred to the destination spacecraft in real time through the parsing process and the output and forwarding process. All devices connected to the onboard bus network of the assembly can send and receive commands mutually. All the manned ships, cargo ships, and other visiting spacecrafts that will be docked with the assembly later can also interact with the onboard assembly seamlessly. On the basis, the complex networks of multi-ship, multi-cabin, multi-spacecraft assembly can be built finally, and the much more complex functions of the space information systems will be realized.
Designs of distributed satellite data management system with wide wireless interconnection.
The traditional remote control and telemetry of satellite is centralized connection and control through the data handle subsystem. Hundreds or thousands of satellite telecommand pulse channels and analog data collection and transmission, so as to realize the controlling and monitoring of the operation status of satellite equipment on the ground, which is provided by one or two centralized devices, which results in a large number of cables to connect the discrete signal and low-speed data of centralized acquisition and control equipment to electronic devices distributed in all corners of the satellite. As a result, the overall assembly and integration of the satellite is more complex, which is not conducive to the rapid production and test of the satellite, and the weight of the cable network that provides the connection for thousands of remote control and telemetry is much heavy. Statistics shows that the weight of the cable network was accounted for about 50% of the weight of the whole satellite. In order to effectively solve this problem, this paper proposed a distributed satellite data management system supporting wireless or wireless wired interconnection for satellite on-orbit assembly, which adopts the distributed I/O model to meet the measurement, control, and low-speed data interface requirement of satellite electronic equipment. The distributed I/O model is installed in each electronic equipment of the satellite, and the relevant discrete telemetry signal interface and low-speed data telemetry interface are converted and packaged into standard data format by the distributed wireless measurement device in each electronic equipment. Multiple distributed wireless measurement and control model from a distributed information network uses wireless wired interconnection interface to pass the information to the satellite computer and send it to the ground. In turn, the uplink control instructions are received by the onboard computer and then transmitted to the distributed measurement and control system, and then sent to the corresponding distributed wireless measurement control module for instruction decoding or given through the low-speed data interface. The distribution I/O model is an important part of information system, which is embedded in the measurement and control signal equipment of spacecraft to provide I/O signal interface service. As shown in the figure above, a distributed I/O model as a satellite microneuron can be used in a variety of flexible ways. That is to say, it can be embedded in each electronic device as the information acquisition and control node, or it can be installed on the whole satellite structure for acquisition and control of multiple small and passive devices. The peripheral technology of the DIO related system is shown in the figure below. The system includes two sets of business. The first bus uses DIO1 as the main uplink channel as the bridge from TTE to CAN bus 1. The telemetry data is transferred and combined to DIO1 according to APID, then sent to the onboard computer, and then sent to the software radio for downlinking through TTE network. In contrast to telemetry, the information flow of remote control data is also distributed according to the APID forwarding table saved in each distributed I/O. Interface design of distributed I/O models. An external interface of the distributed I/O model includes a pair of dual redundant CAN bus interface, 28 voltage control bus interface, 16 channels configurable analog quantity acquisition interface, 16 channels 28 voltage pulse command output interface, 1 wire interface, 4 UART interface, Wi-Fi and wired Ethernet interface. The function design of distribution I/O model is shown below. It includes telemetry signal acquisition, pulse command output, control bus communication, UART interface communication, data and protocol processing, wireless communication function. The function design of distributed I/O model is shown in the figure. The software requirement architecture of distributed I/O is shown in the above image, including interface, processing, forwarding, and other blocks. The following section will make detailed requirement for the function point. The PUS routing processing based on APID function. The application layer software in DIO carries out data forwarding and local-in processing based on the destination APID. If it's an APID processed locally, it will be forwarded to the local-in processing process. In this local-in process, the local-in business processing will be carried out. If the APID is processed locally, is not processed locally, it needs to be forwarded to other devices. The forwarded port and addressing parameters required for forwarding are obtained by querying the DIO APID data processing table, as shown in the right. The communication interface includes CAN bus interface. It can be seen from the figure that there are 2 CAN buses in a system, namely the system CAN bus and the one-to-one locally CAN bus in the wireless charger. Wi-Fi and hot bus communication realize the Wi-Fi self-organizing communication network between the devices on the satellite. Support the wireless connection of the devices on the satellite. Adopt 802.11 protocol standard and the rate is not less than 1 million bps. Wired Ethernet communication. When the distributed I/O model is placed inside the device, the data communication can be upper computer inside the device and the distributed I/O is realized, supporting the 10 million or 100 million bps wired Ethernet communication with supported TCP or UDP communication protocol. UART serial communication. Adopt 3.3 voltage power supply RS-422 3-wired serial support. The bus features are as follows. The camera remote control and telemetry function is realized by adopting bi-direction asynchronous serial communication interface. Communication rate is 115.2 kbps. The implementation result is shown below. Framework of distributed I/O is in the figure below. The system adopted the form of main board plus acquisition subboard, in which the main board is realized by the finished core board plus the customized subband. Acquisition subboard complete telemetry signal acquisition and parse command output, and the operation system is Linux or domestic embedded real-time operating system. The external interface on the backplane include SPI interface for connecting wireless data transmission module and redundant ADC controller. Multiple UART interface for RS-422 communication. A 10 or 100 million bps adaptive Ethernet interface. 2 CAN interface, on-chip ADC interface, and sufficient GPIO pins. In addition to the interface conversion, the baseboard also completes the conversion of external 28 voltage power supply to the 5 voltage power supply of the machine. They provide over voltage, over current, and over temperature protection function for the wall models. Software hierarchy diagram is shown below. The operating system abstracts the data transmission model, RS-422 interface, DDR3 and other interface, peripheral and memory into different types of device and files, realized the relevant device drives, and forms the board-level support package. On the operating system, the application software operates the abstract device through the standard API provided by the operating system. The realized data realizing and interface cooperating of the conversion and power management are discussed to realize the function required by the system. The appearance of the distributed I/O model is shown in the following two pictures. A conclusion: in this paper, a wide wireless distributed onboard data management system is proposed, which is embedded in all kinds of onboard equipment that need to be measured and controlled. The provided interface services such as measurement and control, low-speed series data, one-wire temperature measurement. The distributed interface information management device is used to replace the traditional integrated electronic centralized telemetry acquisition and control architecture to form a distributed satellite information acquisition and control network. The wireless Wi-Fi channel or a standard control bus is used to replace hundreds or even thousands of analog signal cable networks, which make the external interface of the satellite electronic equipment with different forms and functions standardized. It simplified the process of the field integration and assembly. and it's an important support technology for the standardization and rapid assembly of electronic interface of satellite equipment.
Hello everyone. My name is Niu Jiaxiang. This is the presentation of my paper, Research and Implementation of Real-Time Monitoring Technology of Space Constellation Network Status. This paper is directed to the space network and proposes a highly real-time technology scheme for space constellation network status monitoring, which supports real-time acquisition of various types of space network status information. Based on the idea of the integration of the satellite and the ground, the design and implementation of both the satellite and the ground are carried out. My presentation has 4 parts, which are disadvantages of monitoring space status by traditional telemetry, real-time monitoring scheme of space constellation network status, space network status acquisition, testing and verification. The first part, disadvantages of monitoring space status by traditional telemetry. There are 4 disadvantages. First, the huge amount of telemetry data on the entire network poses certain challenges for telemetry reception, storage, analysis, and observation. Second, telemetry information redundancy is a problem. It requires ground extraction before users can obtain information of interest. Third, for space network monitoring, after the initial acquisition of the space network status, the effective information required is the changed network status information, and it is not necessary to obtain all the space network status data. Fourth, telemetry resources are limited on the satellite, and a huge amount of network status information takes up too much telemetry resources. Therefore, it is of great significance to study the use of methods other than traditional telemetry to realize space network status monitoring. The second part, real-time monitoring scheme of space constellation network status. The real-time monitoring scheme of the space constellation network status is integrated design of the satellite and the ground. The IP protocol stack compatible with the ground is operated on the satellite, and a simple network management protocol in the LWIP protocol stack operated on the satellite is supplemented and improved to make sure it can run normally. The space network status information is managed by the satellite, and the ground obtains the network status information of each satellite node of the space network by using simple network management protocol commands. Specifically, first, build an inter-satellite and satellite-ground communication network. Based on TCP/IP protocol stack, the inter-satellite and satellite-ground communication is implemented by using UDP communication protocol. In addition, through the inbound space constellation satellite node, the ground can communicate with any satellite in the satellite constellation, which lays a foundation for the ground to obtain real-time network status information of any satellite node in the space network. Second, complement and improve the simple network management protocol and ensure its normal operation under the LWIP protocol stack to realize space network status monitoring. In the TCP/IP model, the SMP protocol is located in the application layer, which relies on the transport layer UDP protocol for communication. In the process of space constellation network status monitoring, the management station and agent management model are adopted. It is designed to realize the role of agent on the satellite and the role of management station on the ground in this paper. Management station. The management station is an entity that monitors the real-time network status. It is the issuer of commands related to the monitoring status of the entire space constellation network. It sends various management operation commands to the agent and provides space network monitoring personnel operation interface. Agent. The agent is installed on the satellite node of the space network, monitors the working status of the satellite node where it is located, accepts management control commands from the management station, and reports the execution of the commands to the management station. The third part, space network status acquisition. For the satellite part, firstly, design and implement a space network status information dataset, which contains device name, UDP send count, UDP receive count, routing information, and other information data that can represent the current space constellation network status, including space constellation network connection status. Secondly, bind the space network status information dataset with the LWIP protocol stack and routing table running on the satellite, based on the satellite multitask operating environment. Each task circle runs to continuously update and maintain the space network state information dataset. Thirdly, supplement and improve the simple network management protocol for the spatial network status information dataset. In addition, the simple network management protocol is combined with the satellite remote control function to provide the ground with access to obtain space network status information. The spatial network status information dataset is transmitted to the ground in the form of a periodic telemetry by realizing on the SMP command. The ground part. Running the simple network management protocol under the IP protocol stack, realize the SMP get request command and get next request command by remote control commands, and using the ground as a management station to obtain the space network status information of each satellite node in the space network in the form of a cyclic telemetry. In addition, by obtaining the next hop address, the next hop IP address of each network segment can be clearly known. For the ground, The IP of each interface of each satellite is known and determined. Using the fixed network segment address as a clue, query each satellite in transmission path of this network segment. The connection relationship between the satellites can be clarified, and a spatial network connection can be obtained. The specific method of realization of space constellation status information acquisition is shown in this paper. The fourth part, testing and verification. A simple network scenario is built using commercial shelf products to verify the research content of the paper. The constructed network scenario is shown in this figure. There are 3 satellites and a computer in the model. The 3 satellites communicating with each other simulate space network. A computer simulates a ground monitoring equipment. In the above simulation test environment, 3 STM32 development boards are used to simulate 3 satellites, and a computer is used to simulate ground equipment. The 3 development boards are connected to each other through a serial port, and the development board 3 is connected to a computer through a network port. The table shows the network interface configuration of each device. The routing design scheme is shown in this table. According to the simulation test mode established, the operation status of Satellite 2 monitored by ground monitoring software is shown in figure. From the figure, we can see the operation status of the satellite onboard software, and the UDP transmission count is increasing. According to the simulation test modes established, the ground equipment and Satellite 3 are directly connected via a network cable. To test the connectivity of the network, the GET_REQUEST command and the GET_NEXT_REQUEST command are sent to Satellite 1. The device name, UDP receive count, UDP send count of the Satellite 1 are shown in this figure. According to the simulation test mode established, read the satellite onboard routing table, obtain the next hop address of the corresponding route and output it, and get space network connection status. Next hop IP is obtained by using the GET_NEXT_REQUEST command. The result of obtaining the information about next hop IP of all satellites is shown in this table. According to the information we have, the spatial network connection status of the entire space constellation can be obtained. In order to monitor the network status and clarify the spatial network connection status, the following ground monitoring software platform is made to integrate the above functions as shown in this figure. This figure shows the state after standalone acquired button. Facing the booming development of space constellation network, real-time monitoring of space constellation network status is increasingly important. Traditional reliance on telemetry for downlink space network status information has the shortcomings of poor real-time and poor autonomy. This paper proposes the idea of integrating the satellite and the ground, and runs the simple network management protocol under the satellite LWIP protocol stack. Under the premise of maintaining good compatibility with the ground, the realization of monitoring space network status information has high real-time and ultimately obtainable capabilities. That's all my presentation. Thank you very much.